For most of human history, the solar system looked finished. A few lights wandered against the fixed stars. They returned on schedule. The sun rose. The planets kept their paths. Even when they moved strangely, they still seemed to belong to a larger order. Something stable. Something arranged. That illusion survived for a very long time. Because from a human distance, the solar system does look calm. The planets move with such obedience that you can mistake obedience for peace. Their paths are so regular that you can confuse regularity with safety. Seen from the outside, it resembles a diagram, a bright center, clean ellipses, a structure so elegant it tempts the mind into a dangerous conclusion, that this place is settled, well-behaved, fundamentally understood. But the solar system is only calm in the way a scar is calm. What looks orderly now is the surface of something violent enough to have melted worlds, stripped atmospheres, drowned planets in heat, frozen oceans under stone, tipped one giant planet onto its side, and left another kingdom of ice and rock at the edge of the sun's reach like debris that never quite became anything simpler. The serenity is real, but it is late. It is what remains after collisions, migrations, bombardments, magnetic wars, chemical failures, and impossible survivals. From far away, the solar system looks arranged. Up close, it looks survived. And that distinction matters, because nearly every comforting instinct we bring to our cosmic neighborhood is wrong. We imagine the planets as destinations, as if they were places waiting to be understood one by one. Mercury, Venus, Mars, Jupiter, a sequence, a tour. But that is not what they are. They are evidence. Each one is a record of a different negotiation with the same unforgiving laws. Too much heat, not enough atmosphere. Gravity used one way, then another. Water kept, lost, buried, or never allowed to settle. They are not simply worlds. They are outcomes. And the deeper reason this is so unsettling is that Earth belongs to that same set. It is easy to speak of the solar system as though Earth were the default and everything else were a deviation. The dead planets, the failed planets, the strange moons, the inhospitable outskirts. But if you look more carefully, that perspective begins to collapse. Earth does not look central because the system was built around life. Earth looks central because life happened here, and consciousness always starts by mistaking its address for the center of the map. The more we learn about the worlds around us, the less they feel like decorative neighbors and the more they feel like counter-arguments. Venus is what happens when a world too much like ours keeps the heat and loses the future. Mars is what remains when habitability thins into memory. The icy moons suggest that the best places to search for life may not look alive at all. Jupiter is not just a giant planet. It is a machine that may have helped shape the narrow conditions under which Earth remained possible. Even the quietest-looking parts of the system are loaded with old force. What unsettles us is not merely that the solar system is strange. It is that strangeness is the rule, and our idea of normal was provincial from the beginning. Look at the night sky without names for a moment. Strip away the textbook icons, the neat spheres with labeled cutaways, the museum model where each orbit is shown in a different color and every distance is compressed into friendliness. What remains is harder to love quickly and much more difficult to forget. A star burning through its fuel, worlds circling because they cannot escape. Rock, gas, metal, ice, radiation, vacuum. A system held together not by intention, but by gravity and history. History matters here more than beauty does, because what we call the solar system is not just the current arrangement of planets. It is the residue of a much older crisis, before there were worlds with weather or rings or mountain shadows. There was a disk of dust and gas around a young star. Before there were surfaces, there were collisions. Before there were stable seasons, there were impacts large enough to liquefy crusts and rewrite orbits. The peace we now inherit is not primordial. It is negotiated, temporary, dependent on earlier violence having run far enough to leave behind things that can circle for billions of years without tearing each other apart. Even now, without tearing each other apart is only a partial truth. The solar system still keeps its old weapons. Asteroids cross planetary paths. Comets fall inward from darker reservoirs. Giant magnetic fields lash out invisible structures across millions of kilometers. Radiation belts form lethal cages around some of the most alluring worlds we know. Entire oceans may exist where sunlight never reaches. Planets carry ancient injuries in the tilt of their axes, the loss of their air, the silence of their interiors. Some of the most beautiful things in the system are temporary. Some of the most promising things are hidden. Some of the greatest dangers come from the object that makes all life here possible. That is the first fracture in the familiar image. The sun is usually introduced as a source of light, warmth, and gravitational order, all true, all incomplete. It is also a restless plasma engine with moods large enough to rewrite the conditions on every world around it. The solar system does not orbit a lamp. It orbits an active star. And an active star is not a background object. It is an actor. It shapes atmospheres, strips particles into space, floods magnetospheres, drives chemistry, and sometimes reminds every orbiting body that stability is never unconditional. We live so comfortably inside the sun's routine that we forget routine is not the same as gentleness. A morning comes, seasons turn, plants rise into the light. The great machine appears generous. But generosity is only one side of the bargain. The same star that feeds every leaf and ocean on Earth also emits storms of charged particles and magnetic violence powerful enough to expose how thin our safety really is. Not theoretical danger, not mythological fire, just the natural behavior of a star that does not know or care what kind of civilization happens to exist near one of its minor planets. And that is where the solar system begins to change shape in the mind. It stops being a family portrait and becomes a field of conditions. You start to see that every world is living, or failing, under a different version of the same law. Distance matters, mass matters, atmosphere matters, magnetic shielding matters, internal heat matters, the ability to keep water matters, the timing of bombardment matters, the presence of giant planets matters. Even luck matters, though science is usually more comfortable giving luck a better name. Initial conditions, dynamical history, late, heavy delivery, orbital resonance. These are precise phrases. But beneath them is a blunter truth. This system did not owe any planet a future. The reason that truth lands so heavily is that it does not leave Earth untouched. Once you stop seeing the solar system as a calm arrangement of objects and start seeing it as a set of competing planetary fates, Earth becomes harder to read. Our oceans stop feeling inevitable. Our atmosphere stops feeling given. Even the continuity of sunlight begins to look less like a promise and more like a rare balance being maintained for a while inside a much larger mechanism. That does not make Earth less beautiful. It makes beauty harder and therefore deeper. Because the real grandeur of the solar system is not that it contains many spectacular things. It is that beneath the spectacle lies a severe kind of truth. Order can emerge from chaos without ever erasing chaos completely. A world can remain habitable without habitability becoming normal. A system can look serene long after violence has done the work of shaping it. We are not standing inside a finished design. We are standing inside the long afterlife of formation. And once you see that, the planets stop looking like points on a school chart. They begin to look like warnings, relics, experiments, ruins, and narrow escapes. That is where this story really starts, not with distant wonder, but with a loss of innocence, with the recognition that the neighborhood surrounding Earth is not a tidy collection of worlds waiting politely in the dark. It is a record of what the laws of nature do to matter over enough time. Some worlds were stripped nearly to the core, some drowned beneath their own skies, some froze over while keeping their secrets underneath. Some became giant engines of gravity whose influence may have decided which smaller worlds lived long enough to become interesting. And at the center of all of it burns the first great contradiction. The star that made life possible is also the star that can remind every planet around it how provisional survival really is. The contradiction becomes easier to ignore because it arrives as light. Nothing about sunrise feels threatening. It spills across rooftops, across leaves, across oceans that would be black and solid without it. Human life is calibrated so deeply to the sun's regularity that we instinctively place it in the category of constants, not merely important, trustworthy, the oldest clock, the oldest provider, the center that behaves. And in the slow, civil rhythm of ordinary life, that instinct makes sense. The sun is, by every relevant standard, astonishingly stable. It has burned for about 4.6 billion years, fusing hydrogen into helium in its core, holding itself together through a balance that sounds almost too elegant to be dangerous. Gravity crushes inward. Fusion pressure pushes outward. The star survives by continuously preventing either side from fully winning. That equilibrium is why Earth has had the time required for oceans to persist, chemistry to elaborate itself, cells to become ecosystems, and matter to become aware of the fire that feeds it. But stability in astronomy is never the same thing as gentleness, because the sun is not a warm disk hanging in a blue sky. It is a sphere of plasma around 1.39 million kilometers wide, containing more than 99.8% of the mass in the entire solar system. Its core reaches roughly 15 million degrees Celsius. Photons born there do not fly straight out. They scatter, stall, and ricochet through dense solar layers for extraordinary spans of time before finally escaping into space as light. At the visible surface, what we call the photosphere, the temperature is a relatively modest 5,500 degrees Celsius. But even that familiar golden face is deceptive. Above it lies the corona, the sun's outer atmosphere, tenuous and ghostly, and somehow far hotter than the surface below, climbing into the millions of degrees. That paradox is still one of solar physics' great unsolved problems. So even before the sun threatens us, it unsettles us. The object that makes life on Earth possible is not fully understood by the species depending on it. That should already be enough to make the solar system feel less finished than it first appeared. But the deeper disturbance is not hidden in a technical mystery. It is hidden in the way the sun behaves when its magnetic field begins to knot, twist, and break. Because the sun is not made of solid layers rotating together like clockwork. It is plasma, and plasma flows. The equator rotates faster than the poles. Magnetic field lines are dragged, stretched, tangled. Sometimes they reconnect violently, releasing enormous bursts of energy into space. Solar flares erupt. Coronal mass ejections hurl billions of tons of charged particles outward. The solar wind, always present, surges and thickens. Invisible storms spread across interplanetary space. Most of the time, on Earth, we are protected from the worst of this by two shields we barely notice until we imagine losing them. The first is our atmosphere. The second is our magnetic field. The atmosphere catches and disperses radiation, softens cosmic assault, and turns what would be direct exposure into survivable weather. The magnetic field, generated by motion in Earth's molten outer core, extends far beyond the planet itself, forming a magnetosphere that diverts charged particles and helps keep the sun from stripping our atmosphere away, grain by grain. It is not a wall. It is more like a moving negotiation. Pressure from the solar wind compresses the day side of the magnetosphere and drags the night side into a long, magnetic tail. Earth is not sitting safely beneath a dome. It is inside a ceaseless interaction between stellar force and planetary resistance. When that interaction intensifies, the sky itself can become evidence. Auroras are the beautiful version of this truth. Charged particles slide along magnetic field lines into the upper atmosphere, exciting atoms and molecules until they release light. Curtains of green, veins of red, a sky made briefly visible as physics. Seen that way, the northern lights are not just beauty, they are leakage, a reminder that our planet is being touched constantly by the star at the center of the system. Usually, that touch is survivable. Sometimes, it is not mild. In late August and early September of 1859, the sun produced one of the most intense geomagnetic storms ever recorded. The English astronomer Richard Carrington observed a brilliant white light solar flare. About 17 hours later, the disturbance struck Earth. Telegraph systems failed across Europe and North America. Operators received shocks. Some telegraph paper caught fire. In places, lines continued to transmit even after power supplies were disconnected, driven by currents induced directly by the storm. Auroras appeared so far south that skies over the Caribbean and parts of Colombia glowed with colors that should never have been there. People reportedly woke and began preparing breakfast in the middle of the night because the light was strong enough to resemble dawn. That event now bears Carrington's name, but names can make a thing feel smaller than it was. It was not just an oddity in Victorian infrastructure, it was a brief unveiling of dependence, a demonstration that our star can reach across 150 million kilometers and interfere directly with the technological skin of civilization. And the uncomfortable part is not that this happened in 1859. It is that 1859 was, in some ways, a kinder time to be hit. The world then had telegraphy. We have almost everything else: high-voltage transmission networks, satellites for communication, navigation, finance, weather forecasting, defense, undersea cables, aviation systems, digital synchronization, so precise and so deeply embedded that most people never need to think about it at all. A severe geomagnetic storm today would not merely create strange lights and damage wires. It could disrupt power grids, degrade GPS, interfere with satellites, affect radio communications, increase radiation exposure for high-latitude flights and astronauts, and ripple through societies that now run on invisible coordination. The sun does not need to strike Earth physically to remind us that modern life is built inside a stellar environment. We tend to think of space weather as a poetic phrase. It is not. It is weather because it has a medium, dynamics, variability, forecastability, and consequences. It is space because the medium is plasma, magnetism, and radiation moving through a domain we once imagined was empty. Even the phrase carries a conceptual correction. The solar system is not a set of isolated spheres separated by neutral nothingness. It is an active environment. The sun does not simply sit at the center of it, it continuously fills it. That is part of why the old picture of the solar system as tidy planetary architecture fails so completely under modern scrutiny. The planets are not inert marbles circling a static fire. They are bodies immersed in a star's influence to radically different degrees. Proximity matters. Magnetic shielding matters. Atmospheric composition matters. Internal structure matters. A planet close to the sun without a meaningful atmosphere becomes one thing. A similar rocky planet with a dense atmosphere becomes another. A world with weak magnetic protection pays a different price from one with stronger shielding. The sun is the common source. Planetary fate is the variable response, which means the sun is not merely the beginning of the story. It is the first sorting mechanism. The inner solar system makes this brutally clear. Move too close, and light stops being comfort and becomes punishment. Heat becomes not a condition, but a regime. Volatiles struggle to survive. Surfaces crack under thermal extremes. Atmospheres are stripped or transformed. Chemistry narrows. Survival becomes a question of what can endure being held too near the furnace without any appeal, any mercy, any pause. And yet distance alone is not enough to explain what happens. Because the same star that scorches one world can help nourish another. The same radiation that threatens atmospheres also drives chemistry. The same ultraviolet energy that can sterilize exposed surfaces also helps shape the conditions from which complex molecules arise. Nothing in the solar system comes with a simple sign. Safe, unsafe, friendly, hostile. These are not planetary categories. They are human translations of balances that can shift. This is one reason deeper knowledge does not calm the picture. It sharpens it. We start with a childlike image, the sun as source, the planets as recipients. But the real architecture is harsher and more alive than that. The sun floods the system with energy and plasma. Each world meets that flood with whatever tools it happens to possess: mass, air, rock, chemistry, magnetic field, internal heat, orbital distance, luck. What emerges is not a list of worlds, but a distribution of consequences. Earth's consequence happened to include oceans that stayed liquid, an atmosphere that remained substantial without becoming murderous, and magnetic shielding strong enough to keep the stripping pressure of the solar wind from becoming a long-term extinction of possibility. None of those conditions were guaranteed. Each has analogs elsewhere in the solar system, but not in the same combination, not at the same scale, not with the same outcome. Venus kept an atmosphere, but not the kind a surface can survive beneath. Mars may once have had more clement conditions, but it could not hold them. Mercury survived by becoming almost all core. These worlds do not merely orbit under the same sun. They reveal what the same sun does when the planetary answer changes. And even Earth's answer is provisional. The sun itself is evolving, very slowly by human standards, relentlessly by stellar ones. Over immense spans of time, its luminosity increases. The habitable conditions we treat as natural are temporary, long before the sun becomes a red giant, long before it swells outward and transforms the inner solar system beyond recognition. The gradual brightening of the star will alter Earth's climate in ways that eventually make the planet unlivable for complex life. We are not living under an eternal arrangement. We are living inside a favorable interval. That may be the sun's deepest lesson. What sustains life can also define its deadline. This does not make the solar system bleak. It makes it honest. The honesty is what hurts at first. Human perception craves fixed settings, background supports, things that stand outside the drama and make the drama possible. The sun feels like one of those things because its regularity is the precondition for nearly every rhythm we know. But the sun is not outside the drama. It is the largest actor in the inner system. It sets the stage, supplies the energy, imposes the boundary conditions, and occasionally reminds its orbiting worlds that they are still living inside a star's jurisdiction. Once that settles into the mind, the next world inward cannot look like a curiosity anymore. It has to look like evidence. Because if the sun is powerful enough to make even Earth's safety conditional, then the planet closest to it is not just another stop on a tour. It is an exposed test case, a place where survival means enduring the sun without the buffers that make our world feel normal, a world that seems small and simple from a distance, until you realize it may be what is left when a rocky planet is brought too close to the truth. Mercury is where the solar system stops pretending that sunlight is gentle. From Earth, it is easy to overlook. It never dominates the sky. It stays close to the sun, appearing briefly in twilight, low and difficult, as if the innermost planet were trying not to be seen for long. In old observations, it was elusive enough to feel almost secondary, a small world tucked too near the glare to earn the same intimacy as Mars or Venus. Even now, in the public imagination, Mercury often survives as a one-line summary, the smallest planet. The closest to the sun, a scorched and airless rock. But that description misses what makes Mercury unsettling. Mercury is not merely close to the sun. It is what proximity looks like after billions of years. To stand there, if standing were possible in any meaningful emotional sense, would be to inhabit a world stripped down to essentials so severe they barely resemble the planetary normal we instinctively expect. At noon, sunlight is more than 6 times stronger than what reaches Earth. There is no substantial atmosphere to scatter it into softness, no sky to turn it blue, no weather to mediate it, no real cushion between surface and star. The sun would not seem like a radiant presence overhead. It would feel like an occupying force. The light would arrive hard. Shadows would cut like blades. The ground, made of dark rock and pulverized regolith, would absorb and radiate heat so intensely that equatorial daytime temperatures can climb to around 430 degrees Celsius. And then night falls, and the same world drops toward minus 180. That swing alone tells you almost everything about Mercury's condition. It is not simply hot, it is exposed. It lacks the insulating envelope that on Earth smooths thermal chaos into something living systems can survive. On Mercury, day and night are not moods of the same world. They are different regimes, heat without shelter, cold without memory, a planet forced to endure extremes because it has almost nothing left with which to soften them. Even its motion adds to the strangeness. Mercury rotates slowly and orbits quickly, locked into a 3-to-2 spin-orbit resonance. It rotates 3 times on its axis for every 2 trips around the Sun. The result is a rhythm foreign to ordinary intuition. A solar day on Mercury, the time from one sunrise to the next, lasts 176 Earth days, longer than its 88-day year. The Sun in Mercury's sky would not behave with the familiar confidence we take for granted. In some places, because of the planet's orbital eccentricity and rotational geometry, the Sun can appear to rise, pause, reverse course, then rise again. Even daylight refuses simplicity there. This is what makes Mercury more than a burnt stone at the edge of the furnace. It is a lesson in what happens when a world loses almost every buffer we associate with planetary kindness. And yet even that is not the real secret. The real secret is buried much deeper, in Mercury's structure. Because Mercury is absurdly dense for its size, it is a small planet with a disproportionately enormous iron core, one that occupies about 85% of the planet's radius. Strip away the crust and mantle in your mind, and what remains is not a balanced rocky world like Earth in miniature. It is something closer to a metallic remnant wearing a thin skin of silicate rock. Mercury feels less like a complete planet than like a planet after subtraction. That invites one of the great questions hanging over its existence. How did it end up this way? One possibility is that Mercury began as a more conventional rocky planet and then suffered a giant impact early in solar system history, violent enough to blast away much of its outer silicate material and leave behind a core-heavy survivor. Another is that the young Sun, in the violent early phase of the solar system, helped sort material in ways that favored metal-rich survival close in. Or perhaps both processes played a role, initial conditions narrowing what could form there, later impacts finishing the reduction. We do not yet have a fully closed answer, but every viable explanation points in the same emotional direction. Mercury is not simple because it is primitive. Mercury is simple because it may be what remains after complexity was torn off. That difference matters. Primitive worlds feel like beginnings. Mercury feels like aftermath. Its surface supports that feeling. It is heavily cratered, yes, but not in the familiar way of a dead object merely left untouched. The craters are records of punishment layered across geological time, and among them are features that hint at interior change long after the violence of formation. Vast impact basins scar the crust. One of the most famous, Caloris Basin, stretches more than 1,500 kilometers across, a wound so large it reorganized the terrain around it. Elsewhere, great lobate scarps cut across the landscape. Cliff-like structures formed as the planet cooled and contracted. Mercury has been shrinking. Its interior lost heat, its iron-rich body tightened, and its crust buckled in response. So, even in silence, the planet carries tension between old catastrophe and slow inward collapse, a wound that never fully stopped closing. There is something almost severe in the honesty of that geology. On Earth, erosion, plate tectonics, oceans, atmosphere, these things rewrite the surface, bury evidence, recycle trauma into new landscapes. Mercury has fewer ways to forget. It preserves more of the blunt argument gravity and impact made against it. The past stays visible, not because the planet is simple, but because it lacks the machinery of concealment. And still, Mercury refuses to become only a symbol of desolation. That is another reason it matters. Because even here, at the threshold where sunlight feels closest to violence, reality does not flatten into a single note. In permanently shadowed craters near Mercury's poles, where the sun's rays never reach, temperatures remain low enough for water ice to survive. Ice on the innermost planet, not spread across open plains, not gathered in seas, but hidden in cold traps at the bottoms of ancient craters whose geometry allows them to hoard darkness in a world otherwise blasted by relentless light. That contrast is not just scientifically interesting, it is philosophically useful. The solar system does not distribute its secrets according to our instincts. We expect heat to erase water near the sun. Sometimes it does. But under the right local conditions, angle, shadow, topography, time, the impossible-looking thing endures. Mercury is a world where the equator can sear and the poles can keep ice. It is a planet so close to the furnace that noon can melt lead, yet some hollows have guarded cold for eons. Truth in this system is rarely global. It is conditional. The same lesson appears in Mercury's thin exosphere, a ghost of an atmosphere so sparse it barely deserves the name in everyday language. Composed of atoms blasted off the surface by solar wind, micrometeorite impacts, and thermal processes, it is not a protective blanket, but a transient trace, matter constantly lost and replenished. Sodium, potassium, oxygen, helium, hydrogen, atoms lifted, scattered, and swept away. Mercury does not possess an atmosphere in the living planetary sense. It possesses a leak. That image feels right for the whole world. Not a climate, a leak, not a sky, a residue, not a balanced planet, a survivor. And even here, the sun's influence is not total in the simplistic way one might expect. Mercury has a magnetic field, weak compared with Earth's, but real. That alone is remarkable, because it implies that part of Mercury's iron core remains molten and dynamically active enough to sustain a planetary dynamo. The smallest planet, apparently battered nearly down to its metallic heart, still generates a magnetic field of its own. So, the story does not reduce to mere ruin. It becomes stranger than ruin. Mercury is both stripped and internally alive. This is why missions to Mercury matter far beyond the prestige of reaching a difficult world. NASA's Messenger mission transformed our picture of the planet, revealing unexpected chemical diversity at the surface, evidence for volatile elements, signs of a more complex geological history, and the full peculiarity of its magnetic environment. Now, Bepi Colombo, the joint mission of ESA and JAXA, is on its long path toward orbit, promising an even sharper look at the planet's origin, composition, interior, and interaction with the solar wind. We keep returning not because Mercury is the easiest world to summarize, but because it refuses summary. The closer we look, the less it resembles an example, and the more it resembles a boundary case in planetary reality. A world close enough to the sun to be altered by intimacy with it. A world small enough to cool and contract, yet still magnetic. A world apparently stripped, yet not emptied of all complexity. A world hostile enough to seem final, yet still capable of hiding ice in pockets of everlasting dark. Mercury is what the solar system looks like when mercy becomes local. And dos sino that species aspirants. And there is a harder implication beneath that. When we speak casually about whether a planet is habitable or dead, we often smuggle in the assumption that planetary fates come in clean categories. But Mercury pushes against that habit of mind. It is not habitable, certainly. It is not temperate, not generous, not a place where biology as we know it can plausibly build long continuity on open ground. Yet it is not empty of process, not empty of structure, not empty of contradiction. It teaches the first serious lesson of the inner solar system. Closeness to the sun does not merely make a world hotter. It rearranges what kind of world can exist at all. That is why Mercury belongs near the beginning of this descent. Not because it is the smallest planet, but because it is the first world that makes the cost of planetary survival visible. It reveals what happens when a rocky body endures under conditions too intense for softness, too exposed for stability, too close to the source for comfort. It is the innermost audit of what a planet can lose and still remain a planet. Mercury feels less like a world than like a wound that never healed. And if Mercury shows what happens when a planet is stripped by closeness, the next world reveals something even more disturbing. Because Venus was not stripped down. Venus kept almost everything that can turn a planet into a trap. Venus kept the sky. That is what makes it so much more disturbing than Mercury. Mercury is honest from the first glance. It looks severe because it is severe. It gives you rock, crater, glare, and emptiness. Nothing in its appearance invites the comforting fantasy that it was almost home. Venus does the opposite. In mass and size, it is the closest planetary analog to Earth in the solar system. Its radius is only slightly smaller. Its gravity is survivable by terrestrial standards. It is made of rock and metal. It formed in the same inner neighborhood, from broadly similar ingredients, under the light of the same star. If you were choosing a second world by silhouette alone, Venus would seem almost too obvious. That is why it haunts planetary science so deeply. Because Venus is not just another planet, it is the nearest failed version of us. Seen through visible light, its surface is hidden beneath a bright, continuous layer of cloud. To the unaided eye, it can look beautiful, sometimes the brightest object in the night sky after the moon. A steady white brilliance so clean that older cultures naturally linked it with divinity, beauty, love, radiance. Even the modern imagination, despite everything we know, still finds something almost elegant in that brightness. Venus shines with the confidence of a world that appears complete. But the clouds of Venus do not conceal a gentle world. They conceal one of the most hostile surfaces in the solar system. Beneath that pale atmosphere lies a planetary pressure cooker. Surface temperatures hover around 465 degrees Celsius, hot enough to melt lead. The pressure at the surface is about 90 times that of Earth's atmosphere at sea level, the equivalent of being nearly a kilometer underwater in Earth's oceans. Except the fluid crushing you is air. The clouds above are laced with sulfuric acid. The winds in the upper atmosphere move quickly enough to circle the planet far faster than the ground below rotates, while the surface itself remains trapped under a weight of heat and gas so immense that even the distinction between weather and imprisonment begins to blur. Venus does not merely have a harsh climate. Venus has become climate as destiny. That is the deeper horror of it. Not that it is hot, not that it is toxic, but that its conditions are not superficial. They are self-reinforcing. The planet crossed into a state where the atmosphere itself became a machine for keeping the surface unlivable. To understand why that matters, you have to begin with the dangerous innocence of the phrase Earth's twin. The phrase is not false, exactly. It is just incomplete in the worst possible way. Yes, Venus and Earth are similar in size and bulk composition, but twinship in astronomy can hide a catastrophic divergence. Two worlds can begin with enough in common to invite comparison, and still end with one carrying oceans and forests while the other becomes a global kiln under a sky of acid. The similarity is what sharpens the warning. If Venus were obviously alien from the start, its fate would reassure us. But it is not. It is close enough to resemble a fork in the same planetary experiment. A world can look like the beginning of Earth and end like the negation of Earth. At the center of that divergence is the greenhouse effect, one of the most misunderstood ideas in public discussions of planetary climate precisely because the basic mechanism is so simple. Sunlight reaches a planet's surface. The surface absorbs energy and re-emits it as infrared radiation. Certain gases in the atmosphere, carbon dioxide, water vapor, methane, and others, absorb and re-radiate some of that outgoing heat, keeping part of the energy from escaping directly into space. On Earth, this process is not a flaw. It is one of the conditions that make the planet livable. Without a natural greenhouse effect, Earth's average surface temperature would sit far below freezing. But on Venus, that balancing mechanism became something else. Its atmosphere is dominated by carbon dioxide, and it is extraordinarily thick. The greenhouse effect there is not a warming influence laid over an otherwise survivable world. It is the governing principle of the surface. Solar energy comes in. Heat struggles to get out. The dense atmosphere keeps reprocessing that trapped energy until the lower layers become infernal. This is not merely a hot planet. It is a world in which radiative balance has been pushed into a punishing regime. And once enough heating occurs, the danger compounds. If Venus once had significant surface water, and there are serious reasons to consider that possibility, additional warming would have increased evaporation. Water vapor is itself a powerful greenhouse gas. Adding further warming. More warming means more water in the atmosphere, more heat retention, and therefore still more warming. At a certain point, the system stops behaving like a climate that fluctuates around stability and starts behaving like a climate falling through its own floor. This is the essence of runaway greenhouse feedback, a self-amplifying spiral in which heat strengthens the very conditions that trap more heat. That phrase, runaway greenhouse, is often repeated so casually that it begins to sound like a slogan. It is not a slogan. It is a planetary fate. Once a world crosses certain thresholds, recovery is not guaranteed. Oceans can be lost. Water molecules in the upper atmosphere can be split by solar ultraviolet radiation, their hydrogen escaping to space, carbon locked on Earth into rocks, oceans, and cycles can remain in the atmosphere on Venus, sustaining the furnace. Over time, the system becomes harder, thicker, more final. The result is not dramatic in the human sense. There are no flames sweeping visibly across continents, no planetary scream, just pressure, chemistry, and heat doing their work until the surface is less a landscape than a sentence already passed. That is why Venus is so psychologically different from Mars. Mars feels tragic because it seems to have lost something. Venus feels terrifying because it kept going. And there are clues, contested, incomplete, but scientifically serious enough to matter, that Venus may not always have been what it is now. Some models and interpretations suggest that early Venus could conceivably have maintained liquid water for a substantial span of its history, depending on cloud behavior, atmospheric evolution, and the timing of solar brightening. The details remain uncertain, and this is exactly where scientific honesty matters. We do not know with confidence that ancient Venus had oceans like Earth's. We do not know exactly how long clement conditions, if they existed, could have lasted. But the possibility itself is enough to reframe the planet. Because if Venus once held more temperate conditions, then its present state is not merely an alternative design. It is a collapse. That possibility enlarges Venus from hostile planet into something much harder to shake off. Evidence that habitability may not be a stable possession, but a vulnerable interval. A world can be similar in size to Earth, receive energy from the same star, form from related material, and still cross into a regime where the atmosphere no longer protects lifelike complexity, but prohibits it. Under that view, Venus is not just a warning about heat. It is a warning about planetary thresholds. That is one reason modern exploration of Venus has begun to recover urgency after decades of relative neglect. Radar mapping from missions like Magellan transformed our picture of the surface, revealing volcanic plains, deformed terrains, immense lava flows, shield volcanoes, and structures suggesting a geologically active history far richer than the old caricature of a static oven. More recent work has sharpened debates around whether Venus may still be volcanically active today. If it is, then Venus is not just a preserved ruin. It is a live system, still reshaping itself under the same crushing atmospheric burden. That matters, because volcanism is not merely scenery. It links interior heat, crustal behavior, outgassing, and atmospheric evolution. The story of Venus is not confined to the clouds. It runs from the deep interior to the chemical prison above. The planet's rotation deepens the unease in another way. Venus rotates extraordinarily slowly and in the opposite direction from most planets in the solar system. Its day is longer than its year. The sun on Venus would appear to rise in the west and set in the east. Even time behaves there with a kind of estranged awkwardness, as though the planet never settled into the intuitive planetary rhythm our minds expect. The details of how Venus ended up rotating this way remain a subject of study involving tides, atmospheric torques, and ancient collisions. But emotionally, the effect is simple. Even the basic flow of day and night refuses familiarity. And yet, for all this violence of condition, Venus is not easy to read at a glance. That is crucial. It is hidden. Mercury displays its damage openly. Mars displays its loss in dry valleys and dead deltas. Venus hides its catastrophe under brightness. Its atmosphere reflects most incoming sunlight, giving the planet a high albedo and an outward appearance almost of innocence. It is a radiant mask over a crushed surface, a world whose public face is light and whose private reality is pressure. There is something almost too perfect in that deception. The solar system does not only produce dangerous worlds, it produces worlds whose danger is concealed by the very properties that make them visually alluring. Venus shines because it is covered in cloud. Those clouds help hide an environment that would destroy a human being and most of our machines with astonishing efficiency. Soviet Venera landers that reached the surface survived only briefly before the conditions overwhelmed them. Even our technology, engineered with foreknowledge, struggles to endure Venus for long. The planet does not merely reject casual life, it challenges sustained observation. That difficulty is part of why so many unanswered questions remain. How geologically active is Venus today? Exactly how did its water inventory evolve? What was the timeline of its climate transition? How does its atmosphere maintain the extraordinary circulation patterns seen in the cloud tops? How has the interaction between interior processes and atmospheric chemistry changed across deep time? New missions, including Da Vinci and Veritas from NASA and Envision from ESA, are intended to press into these questions, because Venus now matters for more than local curiosity. It matters for comparative planetology, for exoplanet science, for understanding how rocky worlds diverge, and for confronting the dangerous assumption that Earth-like can be judged from size and distance alone. Venus is what happens when a planet keeps all the heat and loses its future. That line lands harder when you realize it is not metaphor. Planets really do have futures in this sense, not conscious futures, not destinies in a poetic register, but sets of physical pathways, some of which preserve complexity, chemistry, and continuity, and some of which crush those possibilities into narrower states. A world with liquid water at the surface can support one range of processes. A world under 90 bars of carbon dioxide at hundreds of degrees Celsius supports another. The transition between those ranges is not just a change in weather, it is a change in what kind of world can exist. Which means Venus is not terrifying because it is exceptional. It is terrifying because it may be lawful. That is the mature form of the fear. Venus is not a monster placed beside Earth for dramatic contrast. It is a physically plausible outcome for a rocky planet under certain conditions. The universe did not break its rules to make Venus. Venus is what the rules did. And once you see that, the old comfort of Earth's apparent normality starts to weaken. A breathable atmosphere, open water, moderate surface pressures, long-term clement conditions, these do not look like defaults anymore. They look like a narrow success inside a much wider landscape of planetary failure. Venus does not just broaden the solar system, it hardens it. Because after Venus, you can no longer pretend that similarity in form guarantees similarity in fate. You can no longer look at a rocky world and assume home is nearby. You can no longer trust brightness. You can no longer confuse atmosphere with safety. You can no longer imagine that the difference between a habitable planet and a sterilizing one must be dramatic from the outset. Sometimes the worst planetary outcomes are not born looking alien, spin-like. Sometimes they begin looking almost familiar. And if Venus is the case of a world that kept too much air, too much carbon dioxide, too much trapped heat, the next world offers the opposite sorrow. Mars is what happens when a planet cannot keep enough. Mars begins where Venus ends, with absence. Not absolute absence, not the clean emptiness of interstellar space, something sadder than that. A world that still has land, seasons, polar caps, dust storms, ancient volcanoes, canyon systems vast enough to shame continents, and yet carries, in almost every one of those features, the impression that more used to be possible here than is possible now. That is why Mars exerts such a hold on the human mind. It is not simply because it is nearby, not simply because it has a surface, not simply because robots can cross its plains and send home pictures that look uncannily like a harsher version of the American Southwest. Mars grips us because it feels posthumous. It is a planet that seems to remember a better version of itself. Venus is frightening because it became too much. Mars is heartbreaking because it became too little. From Earth, it is easy to romanticize that loss. The red color, the deserts, the thin haze, the long shadows on crater rims, the old science fiction fantasy that canals or ruins or civilizations might somehow be waiting beneath the dust. But modern Mars is not compelling because it flatters our imagination. It is compelling because geology has turned the planet into a witness. Valleys, delta deposits, mineral signatures, layered sediments. These are not decorative curiosities. They are records. They tell us, with increasing force and precision, that Mars was once wetter than the world we see now. Not warm and blue in the sentimental Earth-like sense, at least not for all of its history, and not in any way that lets us lazily substitute one planet for the other. The exact climate history of early Mars is still an active scientific problem. There are unresolved questions about how long surface water persisted, how often it flowed, whether conditions were persistently clement or episodic and unstable, how greenhouse warming operated under a fainter young sun, and what role impacts volcanism and atmospheric composition played in producing intervals of runoff and standing bodies of water. But uncertainty here does not weaken the larger truth. It sharpens it. Because even the cautious version of the story is extraordinary. Mars had rivers. Mars had lakes. Mars built deltas. Mars altered minerals in the presence of water. Mars once supported environments far more chemically interesting than the cold, dry, radiation-bathed surface we see today. That is enough to change what the planet means. It ceases to be merely a barren destination and becomes something much harder to face, a case study in lost habitability. This is why the most emotionally powerful images from Mars are often not the most dramatic. Not the giant volcano Olympus Mons, though its scale is almost absurd. Not even Valles Marineris, the canyon system stretching thousands of kilometers like a wound across the planet's face. The images that land hardest are often the quieter ones, an ancient river delta seen from orbit, rounded pebbles indicating long-ago water transport, sedimentary layers stacked like pages, mudstone drilled by a rover that once settled out in a lakebed under a sky thicker than the one above Mars now. Those are not the signs of alien grandeur. They are the signs of a world that crossed a threshold and did not come back. To understand that threshold, you have to think less in terms of scenery and more in terms of planetary retention. Habitability is not only about receiving the right amount of sunlight, it is about holding on to the conditions that allow complexity to persist. Atmosphere, pressure, liquid stability, protection from stripping, internal heat sufficient to maintain some degree of planetary dynamism, time, continuity, on Earth. We tend to experience these as background facts. On Mars, their fragility becomes visible. Mars is only about half Earth's diameter and roughly a tenth of its mass. That matters because size is not cosmetic in planetary science. Size affects gravity, and gravity affects a world's ability to retain an atmosphere over geological time. A smaller planet cools faster. A cooler interior means less internal motion, and less internal motion can mean the weakening or loss of the kind of core dynamics that generate a global magnetic field. Without that field, the atmosphere stands more exposed to the solar wind, not instantly erased, not peeled away in one theatrical event, but gradually worn down, particle by particle, over immense spans of time. A planet does not have to explode to stop being a home. It can simply fail to keep what home requires. Mars appears to have had a global magnetic field early in its history. We know this because parts of the crust retain magnetic signatures, fossil traces of a dynamo that no longer exists. But today, Mars lacks a strong global magnetosphere like Earth's. The shield fell. What remained was local crustal magnetism in patches, not a planetary defense. Meanwhile, the young sun, more active, more violent, would have subjected early Mars to a harsher solar wind environment than Earth experiences now. Over time, the atmosphere thinned, water at the surface became harder to sustain. Lower pressure made liquid water increasingly unstable, tending to freeze or evaporate away. The world that had once hosted flowing water became a world where water could no longer comfortably remain exposed. This is one of the most severe lessons in the inner solar system. A habitable interval is not the same thing as a habitable destiny. There is a temptation, when talking about Mars, to lean too heavily on a single explanatory key. It lost its magnetic field. Therefore, it lost its atmosphere. Therefore, it lost surface water. There is truth in that chain, but the full story is more textured and more honest than any one-line collapse. Volcanic outgassing, impact history, atmospheric chemistry, obliquity cycles, crustal interactions, and the precise timing of climate transitions all matter. Some water did not simply vanish into space. Some became locked in minerals. Some froze into polar deposits or subsurface ice. Some retreated underground. Mars did not die in one way. It became less habitable through multiple losses interacting across time. That complexity is not a weakness in the narrative. It is the narrative. Because the deeper reality is not that Mars suffered one fatal blow, it is that planetary failure can be cumulative. A world can become less buffered, less warm, less wet, less protected, less geologically alive, until the conditions that once allowed one kind of chemistry to flourish narrow into something harsher and thinner. Mars is not the fossil of a catastrophe alone. It is the fossil of attrition. And attrition is harder to dramatize, but more frightening to understand. It means worlds can decline without spectacle. They can become inhospitable by degrees. They can lose the future slowly enough that no single moment deserves the title of ending. That may be one reason Mars feels so intimate to us. Its failure was not flamboyant. It was procedural, a set of physical disadvantages working patiently over time. The modern surface reflects the patience everywhere. The atmospheric pressure is less than 1% of Earth's at sea level. The air is mostly carbon dioxide, but too thin to provide the kind of greenhouse warming that would make open, stable liquid water common at the surface now. Radiation reaches the ground more directly because there is no thick atmosphere and no strong global magnetic shield. Dust can be lifted into storms that engulf the whole planet. Yet the air doing the lifting is itself astonishingly tenuous. Even wind on Mars feels paradoxical, capable of reshaping dunes and coating machinery, while remaining too insubstantial to feel anything like weather on Earth. And yet Mars is not inert. That is part of its hold on us. The polar caps grow and retreat seasonally. Dust devils trace temporary calligraphy across the plains. Methane measurements have periodically provoked debate, though their interpretation remains unresolved, and caution is essential there. Seismic data from NASA's InSight mission revealed that Mars is still internally active enough to produce Marsquakes, offering a new view into crust, mantle, and core structure. Subsurface ice is widespread. Ancient hydrothermal environments may once have existed in places where water, heat, and rock interacted. The planet is not alive in the biological sense we mean when we talk about ecosystems, but it is not dead in the simplistic sense either. Mars remains a system. It still changes. It still hides. That is why so much of the best Mars science has converged on an apparently modest question with enormous consequences. Not, is Mars like Earth, but where, when? And for how long did Mars provide conditions under which life could have emerged or persisted? That change in framing matters. It replaces fantasy with discipline. It also makes the planet more interesting, not less. Rovers like Spirit, Opportunity, Curiosity, and Perseverance have not merely been sightseeing machines. They have been field geologists reading a broken climate archive. Perseverance, in Jezero Crater, is exploring an ancient delta where sediment once entered a standing body of water. Curiosity, in Gale Crater, has traversed layers recording changing environmental conditions over time. These missions matter because Mars keeps the memory of habitability in stone. Mars is not the dream of a second Earth. It is the fossil of a first attempt. That line is not literally historical. Earth and Mars formed in parallel. Not in sequence of value, but it captures the emotional truth of comparative planetology. Mars shows that rocky worlds can come close. They can have water, weathering, sedimentary environments, energy gradients, chemical complexity, and still they can fail to sustain the broader architecture long enough for the story to deepen. This is why human plans to go to Mars always carry a strange double charge. On one level, Mars is the obvious frontier, reachable, terrestrial in texture, scientifically rich, culturally loaded. On another level, Mars is a warning against superficial resemblance. A horizon is not an invitation. A landscape is not a refuge. The fact that a human boot could one day stand there does not mean the planet ever wanted to become a home. Mars can be explored, inhabited temporarily in engineered systems, perhaps altered in limited ways by future technology, but none of that should blur the planetary truth written into it. Left to itself, Mars is what a near-habitable world looks like after the conditions that once softened it have largely withdrawn. And that withdrawal did not erase everything. It preserved evidence with brutal generosity. Dry river channels remain because no active hydrological cycle has erased them. Ancient deltas persist because the atmosphere no longer supports the water needed to remake them. Surface minerals store memories of water chemistry that on Earth would often be recycled through plate tectonics and weather. Mars, like Mercury in a different register, has fewer ways to forget. Its losses became a kind of archive. That archive is one reason the search for past life on Mars remains scientifically serious. Not because scientists are smuggling certainty into hope, and not because every ambiguous result deserves breathless headlines, but because the ancient environments were real enough, persistent enough, and chemically interesting enough that the question is worth asking with care. If life ever appeared there, even in microbial form, traces might remain in sedimentary structures, mineral contexts, isotopic patterns, or organic preservation niches. Nothing about that is guaranteed. Nothing about it licenses sensational claims. But the possibility is grounded, not theatrical. Mars asks a painful question with unusual precision. How long does a world have to stay favorable before chemistry becomes history? We do not yet know, but Mars is one of the best places in the solar system to try to find out. And that is exactly where the emotional pressure of the story changes. Because up to this point, the inner planets have shown us three versions of proximity to the Sun. Mercury, too exposed. Venus, too trapped. Earth, balanced. For now. Mars introduces something subtler, and in some ways more haunting than either furnace or wasteland. It shows that habitability can recede. A world can once permit one class of possibilities and later deny them. Not because the laws changed, but because the balance did. Once you absorb that, Mars becomes harder to keep in the category of dead planet. Dead is too simple. Dead sounds complete. Mars is not complete. It is interrupted. A planet whose early promise did not hold. A climate that narrowed. A surface that remembers. A world standing just beyond the line where familiarity might have continued. And if Mars teaches the sorrow of lost habitability, the next turn in the descent does something more destabilizing still. Because it reveals that life's best chances in the solar system may not belong to planets with open skies at all. They may belong to worlds hidden under ice, under pressure, under darkness, far from the sun, but kept awake by something else entirely. That possibility would already be strange enough on its own. But the solar system rarely settles for one unsettling revision at a time. Because the moment you begin to accept that Mars may be the afterimage of a habitable world, another question rises beneath it. What if we have been asking the wrong kind of body to carry the burden of life all along? What if the most promising environments in our cosmic neighborhood are not open landscapes under visible suns, but sealed interiors, warmed from within, hidden under shells of ice or radiation or darkness so complete that the old Earth-centered image of habitability no longer applies? That renewal in the story begins with Jupiter. From Earth, Jupiter seems almost too obvious to be mysterious. It is the giant among the planets, the most visually commanding after Venus, a banded sphere so large that calling it a world can feel, at times, like an understatement. It has dominated myth, naked-eye astronomy, and modern images with equal ease. Even people who know almost nothing about planetary science usually know Jupiter is the biggest. But size, in the solar system, is never just spectacle. Jupiter contains more than twice as much mass as all the other planets combined. If the solar system is a gravitational drama, Jupiter is the dominant secondary character, the one whose presence changes the shape of everyone else's fate, even when the camera is pointed elsewhere. It did not merely form within the young solar system. It helped organize the young solar system. Its gravity stirred planetesimals, redirected debris, sculpted resonances, influenced the architecture of the asteroid belt, and likely affected how volatile-rich material moved through the system. Depending on the era and the model, Jupiter may have helped shield the inner planets from some impactors while also driving dangerous material inward under other circumstances. It is not a simple guardian. It is an agent of selection. Jupiter did not simply protect our story. It helped write the dangerous opening chapters. That is what makes the planet so conceptually powerful. Human imagination prefers cleaner roles: protector or threat, benefactor or destroyer. But Jupiter belongs to the harder category that planetary science keeps forcing on us: world-making through ambiguity. It may have reduced some classes of catastrophic impacts on Earth over long timescales. It may also have contributed to the delivery or redistribution of icy material and other volatiles essential to the chemistry of the inner planets. And in the early solar system, when young worlds were still forming, colliding, and differentiating, Jupiter's immense gravity would not have acted as a passive backdrop. It would have rearranged probabilities. That matters because probability is another name for fate when you stretch time far enough. To understand Jupiter properly, you have to stop thinking of it as a bigger planet and start thinking of it as a planetary machine. It is mostly hydrogen and helium, but those familiar elements do not remain familiar under Jovian conditions. Descend through the cloud tops and the atmosphere thickens. Pressure builds, chemistry shifts. The visible bands, those pale zones and darker belts, are only the upper expression of deep convective and dynamical processes. Below them, hydrogen is compressed into exotic states. Deeper still, under pressures difficult to visualize, honestly. Hydrogen is thought to become metallic, behaving not like a molecular gas, but like an electrically conducting fluid. In that strange interior, motion generates Jupiter's colossal magnetic field. The result is one of the most severe environments in the solar system. Jupiter's magnetosphere is enormous, extending millions of kilometers into space and forming a magnetic domain so vast that, under the right conditions, it would appear larger than the full moon in Earth's sky if human eyes could see it. This is not a decorative field. It traps charged particles with ferocity, creating radiation belts lethal enough to complicate spacecraft operations and redefine what nearby means for the moons moving within that system. To orbit Jupiter is not simply to circle a planet. It is to move through an active electromagnetic empire. And still, all of that is only the beginning. Because Jupiter's most famous visible feature, the Great Red Spot, has done more than decorate telescope eyepieces for centuries. It has taught us how misleading planetary familiarity can be. At a glance, it looks like a stain, a mark, perhaps a surface feature. In reality, it is a storm, an anticyclonic vortex larger than Earth, persisting for centuries, embedded within a larger atmospheric system, whose motions dwarf any weather humans have ever known. The winds racing through Jupiter's atmosphere can exceed hundreds of kilometers per hour, and, unlike storms on Earth, they are not constrained by solid ground below in any simple way. There is no surface to land on, no stable terrain where atmosphere cleanly ends and world begins in the intuitive terrestrial sense. Jupiter forces a philosophical correction before it forces a scientific one. A planet does not need a surface to have weather. A world does not need solidity to have structure. A giant can be made mostly of gas and still dominate the destinies of stone. This is what makes Jupiter such a turning point in the script's deeper argument. Up to now, the inner planets have taught us about different failures or survivals of rocky worlds under the sun. Jupiter changes the scale entirely. It reminds us that the solar system is not built only out of places where a human imagination can stand and look around. Much of its real architecture is imposed by bodies so large, so dynamically powerful, and so unlike Earth that the very categories of familiar planetary thought begin to fail. And yet even that is not Jupiter's deepest role in this story. Its deepest role lies in how it changes the meaning of the moons around it. Because if Jupiter were only a giant atmosphere surrounded by lethal radiation, it would still be extraordinary, but it would not yet force the full revision this story needs. The real revision comes when you look at its satellites and realize they are not merely ornaments of a giant planet. They are entire environments shaped by gravity in ways sunlight alone could never explain. Jupiter does not just possess moons, it energizes them. This becomes obvious first with Io. Io is one of the most hellish bodies in the solar system, and one of the most scientifically clarifying. At a glance, the colors already feel wrong. Yellow, black, orange, white, sulfurous tones splashed across a surface that looks less like rock than chemistry under stress. But the real violence is not in the appearance. It is in the engine beneath it. Io is the most volcanically active world we know. Not because it sits especially close to the Sun, but because Jupiter and the orbital resonances with neighboring moons continuously need it gravitationally. Its orbit is not perfectly circular. That matters. The slight variation in distance during each orbit means Jupiter's immense gravity flexes Io's interior over and over again. Rock heats under that repetitive strain. The whole moon becomes a body worked by tides so intensely that the heat escapes as magma and sulfur-rich plumes that can rise hundreds of kilometers above the surface. Io is a world where gravity behaves like friction. That single realization does more than explain one moon. It breaks an old assumption about habitability itself. Because for so long, human thinking about life-bearing worlds was tied almost automatically to sunlight. A world receives energy from its star, maintains liquid water in the right range of temperatures, and chemistry does the rest if enough time is available. That model remains crucial. It explains Earth, it guides exoplanet searches. It is not wrong. But Jupiter's system reveals that it is incomplete. Energy can come from other places. A world can be heated from the inside, not only from above. A moon far from the Sun can remain geologically active because gravity is doing work inside it. And once that principle exists, Europa becomes unavoidable. If Io is the violent version of tidal heating, Europa is the haunting one. From a distance it looks almost austere, a bright, smooth globe etched with long, dark lines, as though the surface were made of porcelain beginning to crack. Compared to crater-heavy worlds, Europa appears strangely young. That apparent youth is itself a clue. Surfaces in the solar system accumulate scars over time. To remain relatively smooth, a surface must be renewed. On Europa, the dominant view is that an outer shell of water ice lies above a global subsurface ocean, with tidal heating from Jupiter helping keep that ocean from freezing solid despite the moon's great distance from the Sun. The implications are enormous and very carefully bounded. A global ocean does not mean life. Internal heat does not mean biology. Water is a condition, not a conclusion. Scientific discipline matters most precisely where wonder is strongest. But the ingredients on Europa are enough to elevate it into one of the most compelling astrobiological targets in the solar system: liquid water, an energy source, and a rocky seafloor below the ocean where water-rock interactions may occur. That combination is not proof of living systems. It is something subtler and more powerful for a scientist: plausibility. The old picture of life needing a blue sky and temperate sunlight begins to fail here. Europa may contain more water than Earth, and yet almost all of it is hidden under ice and permanent darkness. No forests, no open shorelines, no breathable air, no visible invitation. If life exists or ever emerged in such a place, it would do so far from the conditions human intuition once treated as normal. That is why Europa feels less like another moon, and more like a quiet insult to our provincial imagination. The solar system may have been constructing habitable niches in silence, under frozen shells, while human beings spent centuries staring only at surfaces. The most alive-looking worlds may be dead on the surface, and the most promising ones may hide everything that matters below it. This is the real midpoint ignition. Because now the script is no longer just about how planets fail. It is about how reality outgrows the categories we first brought to it. Mars taught us that habitability can be lost. Jupiter and its moons teach us that habitability may also be displaced, moved out of the sunny, open, Earth-like settings we instinctively prioritize, and into places where gravity, chemistry, and darkness collaborate in ways almost no early cosmology could have anticipated. It also changes the emotional tone of the solar system. The system becomes less like a map of surfaces and more like a map of hidden interiors. The visible face of a world matters less. What matters now is what lies beneath. Molten metal, trapped heat, subsurface oceans, flexed rock, buried chemistry. The truth retreats inward. If you want to understand these places, seeing them is no longer enough. And that shift has a consequence for Earth as well. Because once you allow that life-friendly conditions might exist inside frozen moons orbiting a giant planet far beyond Mars, then Earth stops looking like the singular template and starts looking like one successful expression of a broader physical principle. Wherever energy, chemistry, and persistence overlap under the right constraints, complexity may have a chance, not a guarantee, not a promise, a chance. And chance is already more than the old, narrower picture allowed. Jupiter's radiation belts, its crushing interior, its endless storms, these are not distractions from that lesson. They are part of it. The giant that may have helped make Earth's long survival possible also presides over some of the most extreme environments we know, and around it circle moons that may hold concealed oceans under locked crusts of ice. Jupiter is not a world in the comforting sense. It is a system within the system, a sovereign zone of pressure, force, and possibility. It taught the solar system to become larger than sunlight. And once that thought enters, the next movement becomes impossible to resist. Because Jupiter is not the only place where hidden oceans and buried chemistry begin to erode our older ideas of where life, beauty, and planetary meaning are supposed to live. Beyond it waits another realm, colder and more outwardly serene, where one of the most beautiful objects in the sky turns out to be something even more severe than beauty. Not permanence, not decoration. Debris, balance, and loss made briefly luminous. Saturn looks, at first, like the reward for believing the solar system is beautiful. Not merely beautiful in the technical way astronomers use when they mean elegant structure or compelling morphology. Beautiful in the older, more dangerous way. The kind that tempts the mind into softness, a pale golden sphere suspended in blackness, girdled by rings so perfectly proportioned that they seem less like matter than like an idea of order made visible. Even people who know almost nothing about planets can recognize Saturn at a glance. It has that rare power of appearing immediately symbolic. It does not simply look like a world, it looks like meaning. And that is exactly why Saturn needs to be understood more carefully. Because Saturn's rings are among the most powerful visual deceptions in the solar system. They look eternal. They are not. They look solid. They are not. They look serene. They are not. They look like architecture. They are really process. If Jupiter forced us to accept that worlds can be shaped by hidden interiors and violent gravitation, Saturn does something subtler and in some ways more devastating. It takes one of the most graceful things we can see through a telescope and reveals that grace to be made of fragmentation, collision, sorting, and eventual disappearance. The lesson is no longer merely that the solar system is violent beneath appearances. It is that some of its most exquisite appearances are violence made orderly for a while. Saturn's rings are not a shell, and they are not a solid disk. They are an immense, astonishingly thin system of countless particles, mostly water ice, with some rocky material mixed in, ranging in size from dust grains to chunks meters across, and larger, from far away. They merge into a luminous plane. Up close, they resolve into a crowded orbital society of separate objects, each obeying gravity, colliding, clustering, scattering, exchanging momentum, and participating in a structure that looks static only because the eye cannot follow a billion local motions at once. That is one of the deepest truths in planetary science. Stillness is often just motion seen from too far away. The rings stretch outward for hundreds of thousands of kilometers, yet in many regions they are astonishingly thin relative to that width, often on the order of the tens of meters. If you built a model scaled honestly enough, the proportions would stop looking like a broad shield and start looking like something closer to a blade, a sheet, a luminous cut laid around the planet. Saturn does not wear a halo. It wears an instability flattened into brilliance. And the flattening is the point. The rings exist because matter there, is trapped in a difficult compromise. Too close to Saturn, tidal forces can prevent loose material from accreting into a larger moon. Too far, and aggregation becomes more plausible. In the region of the rings, gravity and disruption are locked in a kind of argument. Particles can gather into temporary structures, wake-like patterns, braided edges, and clumps. But large-scale consolidation is resisted. The ring system is not a finished object. It is matter prevented from becoming something simpler. That makes the beauty harder. Because once you understand that, the rings stop feeling ornamental. They begin to feel suspended between possibilities, no longer a moon, not merely dust, not permanent architecture, but debris held in a dynamically constrained state. A moon torn apart, perhaps, material left over, perhaps, a younger structure than we once assumed, perhaps. Saturn's rings still carry serious scientific debates around their age and origin, and that uncertainty matters. Some evidence has suggested the main rings may be surprisingly young in cosmic terms, potentially on the order of hundreds of millions of years, rather than dating back unchanged to the birth of the solar system. Other models and constraints complicate that story. The details remain actively studied, but what matters narratively is not false certainty. It is the direction of the truth. Whatever their precise age, the rings are not outside time. They are changing. Cassini made that impossible to ignore. Before its mission ended in 2017, with the deliberate plunge into Saturn's atmosphere, the spacecraft transformed the rings from a distant icon into a lived physical system. It saw structure within structure, density waves, propeller-like disturbances caused by embedded moonlets, shepherding effects from nearby moons, fine-grained texture written by resonance and collision. It also helped reveal something more melancholy. Ring material is not simply orbiting forever in untouched perfection. Some of it is being lost. Ice and dust can be pulled inward along magnetic field lines and fall into Saturn's atmosphere as what researchers call ring rain. The rings, in other words, are not only there, they are draining. Saturn's rings look eternal only because we are watching them in the brief moment they still exist. That is one of the coldest and most beautiful sentences the solar system writes about itself. We came late enough to see them, but perhaps not so late that they are gone. Human beings may exist in a narrow historical interval during which Saturn carries this particular visible grandeur. For most of the age of the solar system, perhaps the rings were different, smaller, absent, or not yet in their current form. In the future, they may thin, darken, disperse, or disappear into Saturn entirely. The object that has defined Saturn in every child's drawing and every amateur telescope may be a temporary condition. A masterpiece with an expiration date. That realization does not make Saturn uglier. It makes it almost unbearably more beautiful, because beauty becomes inseparable from transience. We are not looking at a symbol of permanence. We are looking at a dynamic structure that owes its elegance to a temporary arrangement of ice, gravity, resonance, and time. It shines because sunlight catches shattered water. It persists because orbital mechanics keep destruction and reassembly in a tense equilibrium. It will not remain exactly as it is. The rings do not decorate Saturn, they expose time. And once time enters, the whole system deepens. Because the rings are not isolated from Saturn's moons, they are in conversation with them. Tiny shepherd moons influence ring edges, confining particles and sculpting narrow bands. Larger moons participate through orbital resonances, creating waves and gaps that look from a distance, like deliberate design. The famous Cassini division, one of the most prominent dark gaps between major ring groupings, is not an empty slash produced by aesthetic instinct. It is part of a dynamical story involving orbital relationships, especially with the moon mimas. The ring system is full of such interactions. Meaningful emptiness, in astronomy, is often structure under another name. That too is a correction of intuition. We tend to think of emptiness as blankness. In Saturn's rings, emptiness can be an active product of force. Gaps are not necessarily where nothing happened. They are where motion has been organized. A resonance clears, sculpts, destabilizes, or confines. Seen properly, even the spaces in the rings are consequences. And that is why Saturn belongs so naturally after Jupiter in this descent. Jupiter taught us that gravity can build hidden oceans under ice. Saturn teaches us that gravity can turn destruction into lace. The same laws, a different kind of severity. There is another reason the rings matter so much in this story. They help strip away the last trace of the old idea that the solar system's grandeur lies in large objects alone. By mass, Saturn's rings are negligible compared with the planet itself. They do not define Saturn dynamically in the way Saturn defines them, and yet to the human eye and imagination, they dominate the entire world. This mismatch is revealing. It tells us that significance in the solar system is often not where scale alone would place it. Thin structures can carry enormous meaning. Fragile-looking arrangements can encode deep physics. What appears secondary can become the emotional center. That principle is about to matter even more. Because Saturn's most interesting secrets are not the rings. The rings are the threshold, the invitation, the visible grace that allows the deeper correction to arrive. Beyond them move moons that take the lesson of hidden interiors and buried chemistry even farther than Jupiter's did. If Europa suggested that a dark ocean beneath ice might still hold some chance for life, Saturn's system offers two worlds that widen that possibility in entirely different directions. One is Titan, wrapped in a dense orange atmosphere, with rivers and lakes not of water, but methane and ethane under a sky thick enough to hide the surface from ordinary sight. The other is Enceladus, small and brilliant and seemingly modest, except that it vents material from a subsurface ocean through fractures in its icy crust into open space itself. One moon rewrites what a landscape can be. The other ejects evidence from a hidden sea like a confession. And suddenly Saturn's rings acquire a new role in the architecture of the story. They are not the destination. They are the last beautiful simplification before chemistry gets stranger. Because if the rings show that beauty in the solar system can be made of matter already being lost, Titan and Enceladus suggest something even harder to absorb, that worlds far beyond the old habitable zone may not merely preserve water or structure, but may sustain active environments where some of the prerequisites for life are not hypothetical abstractions. They are present, measured, sampled, still unfolding. The solar system keeps doing this. It keeps moving the center of seriousness away from where instinct first places it. A giant planet turns out to be a system-shaping machine. A cracked icy moon turns out to be an ocean world. A perfect ring turns out to be temporary debris. And now, beyond those luminous bands, two moons wait to make open sky feel less central to habitability than buried chemistry, internal heat, and time. Saturn's rings are beautiful because they are unstable. What comes next is more unsettling. It may be alive for reasons we were never taught to expect. Titan begins as a visual refusal. Even in the age of high-resolution imaging, when so many worlds in the solar system have surrendered their surfaces to cameras, Titan still greets the eye as concealment, a globe the color of old amber, soft-edged, veiled, not the bright reflective cover of Venus, not the bare glare of Mercury, not the clean ice of Europa. Titan looks submerged in its own atmosphere, as though the moon has withdrawn behind chemistry so completely that surface and sky can no longer be separated at a glance. That opacity is not incidental, it is the key. Titan is the only moon in the solar system with a dense atmosphere, and not merely dense by the standards of a small icy satellite. Its atmospheric pressure at the surface is actually greater than Earth's. But the atmosphere is not made into familiarity by being thick. It is made stranger by what it contains. Mostly nitrogen, like Earth's, which at first sounds like an invitation to comparison, but mixed into the nitrogen are methane and more complex hydrocarbons, participating in a chemistry driven by sunlight and energetic particles high in the atmosphere, producing haze layers and organic compounds that settle downward through the cold. What reaches the surface is a world that, in some formal ways, resembles Earth. Rain, rivers, lakes, erosion, seasonal cycles, while in physical substance it is almost entirely other. Titan is not an imitation Earth. It is Earth's logic translated into alien materials. At its surface, Temperatures hover near minus 179 degrees Celsius. Water there behaves not like liquid but like rock. Methane and ethane, which on Earth would be gases, can exist as liquids. The result is one of the most conceptually disorienting landscapes in the solar system. River channels carved not by water but by hydrocarbons. Lakes pooled under a dim orange sky. Possible rain-feeding drainage systems. Dunes built not of quartz sand but of organic particles and dark grains shaped by winds moving through a dense, frigid atmosphere. This is not merely a curiosity in planetary chemistry. It is a direct assault on the instinct that familiar processes require familiar substances. On Earth, when we say river, we bring with it a whole package of assumptions: liquid water, erosion in a narrow thermal regime, weather under a breathable sky, geology organized by the chemistry of our own planet. Titan strips away the substances while preserving much of the pattern. Liquids still fall, channels still cut, lakes still gather in basins, shorelines still matter, weather still exists. A hydrological cycle remains, but not hydrological in the terrestrial sense. Methane rises, condenses, precipitates, flows, evaporates. The same broad logic survives. The matter changes. The meaning of planet-like changes with it. That is one reason Titan matters so much scientifically and philosophically. It broadens the category of what a world can be without reducing it to abstraction. It does not just tell us that alien environments exist. It lets us see one. Radar mapping and data from the Cassini-Huygens mission revealed river valleys, dune fields, polar lakes, and seas, and a surface varied enough to feel eerily coherent under conditions that should, by human intuition, abolish coherence. Huygens descended through Titan's haze in 2005 and returned images from a landscape of channels and rounded ice cobbles at the surface, a shoreline-like world where the analogy to Earth was undeniable even though the materials were almost entirely wrong for that analogy. Wrong for us, at least right for Titan. That distinction is where the moon acquires real force. Titan is not bizarre because it breaks the laws of planetary behavior. It is bizarre because it obeys those laws under conditions our instincts never evolved to expect. Energy gradients, condensation cycles, atmospheric transport, surface-atmosphere exchange, these remain. The system is lawful, but the lawfulness does not comfort us, because it reveals how contingent our own version of normal really is. And then the story deepens again. Because Titan's surface chemistry, remarkable as it is, may not be the whole of its astrobiological interest, beneath the icy crust, there is strong evidence for a subsurface liquid water ocean, not at the surface where methane lakes lie, but below, where interior heat and chemical conditions may sustain an entirely different environment. This gives Titan a two-layered strangeness. On top, hydrocarbon weather and frozen water geology. Below, the possibility of a hidden water ocean, one moon carrying two different world logics at once. That is hard to overstate. Titan does not simply offer one alternative to Earth. It offers stacked alternatives, a surface world run by methane under a nitrogen sky, and perhaps a deeper interior world where liquid water persists under ice. It is as if the solar system, having already shown us with Europa that an ocean may survive in darkness, now adds the further insult that an alien moon can also have lakes, rivers, rain, and climate, just not in the chemistry we were taught to treat as central. The implications are disciplined, not sensational. Titan is not evidence of life, nothing in its atmosphere, lakes, or hidden ocean licenses that leap. But Titan is an extraordinary natural laboratory for prebiotic chemistry and comparative planetary behavior. Complex organic molecules form in its atmosphere. Surface and atmospheric processes are active. Energy flows, materials cycle. The moon shows, at planetary scale, how chemistry can become environment. For scientists interested in the origins of life, or in the range of pathways by which complexity can arise short of life, Titan is not a sideshow, it is a serious place. And that seriousness is about to become even more literal. NASA's Dragonfly mission, planned to explore Titan from the air with a rotorcraft, exists because Titan's atmosphere, low gravity, and scientific richness combine into something rare, a world where flight is practical and chemistry is worth chasing across vast distances. Dragonfly is not going to Titan because Titan is picturesque. It is going because the moon preserves questions too large for orbit alone. How far can prebiotic chemistry go in such an environment? What is the detailed composition of the surface materials? How do atmosphere, organics, and crust interact across time? Titan invites exploration not because it resembles Earth, but because it does not. But if Titan is the moon that broadens the imagination, Enceladus is the moon that tightens it. Because Enceladus is small, bright, easy to underestimate, in a more superficial version of this story, it would have remained a minor icy satellite among many. And then Cassini flew through the plumes. That changed everything. At Enceladus' south pole, giant fractures, often called tiger stripes, cut through the ice. From these fractures, jets of water vapor, ice grains, and other material erupt into space, not metaphorically, not as a speculative reconstruction. Actually, material from the moon's interior is venting into vacuum. Cassini sampled those plumes directly and found water vapor, salts, organic compounds, and, crucially, evidence consistent with hydrothermal activity on the floor of a subsurface ocean. Tiny silica grains detected in plume material pointed toward interactions between water and warm rock at depth. Molecular hydrogen, also detected, strengthened the picture of an active seafloor chemistry. This is one of the most remarkable discoveries in modern planetary science. A small icy moon, orbiting far from the Sun, appears to harbor a global subsurface ocean in contact with a rocky core, with internal heating sufficient to maintain activity and plume material generous enough to throw samples of that hidden world into space for passing spacecraft to analyze. Enceladus does not merely conceal an ocean. It leaks habitability into the void. Again, that word must be used with discipline. Habitability does not mean inhabited. A potentially habitable environment is one in which some of the known prerequisites for life as we understand it may be present. Liquid water, a source of energy, access to essential chemical elements, and some degree of persistence. Enceladus appears to satisfy these conditions in ways far more concrete than anyone expected before Cassini. That makes it one of the most compelling targets in the solar system for future astrobiological investigation. It does not make it a proven biosphere. Precision matters, but precision does not diminish the wonder. It refines it. Because once you understand what Enceladus is offering, the old mental map of the solar system becomes almost unusable. A world smaller than the moon, sheathed in ice, orbiting a ring giant in the outer solar system, may contain one of the best places we know to look for life beyond Earth. Not because it has sunlight and continents and open seas, because it has hidden water, geochemical energy, and direct access to its own interior through jets blasting into space. This is what the solar system keeps doing to us. It keeps relocating significance. We start with planets because planets feel important. We privilege surfaces because surfaces are where human beings stand. We privilege sunlight because sunlight is what fed every ecology we know. Then the system answers with Titan and Enceladus. One says a world can have weather, rivers, lakes, and climate in a chemistry almost nothing on Earth could survive. The other says a dark ocean under ice can be more astrobiologically compelling than many open, sunlit landscapes. The deeper lesson is not simply that alien life, if it exists, might be weird. It is that the physical conditions allowing complexity may be distributed in forms our instincts almost systematically underrate. That should change how Earth looks as well. Because Earth's greatness lies not in being the only possible format for meaningful planetary complexity, but in being one successful arrangement among a wider family of lawful possibilities. Some worlds preserve open water and oxygen-rich atmospheres, others preserve methane cycles, others hide oceans in darkness, others fail entirely. The solar system is not a ladder with Earth at the top. It is a branching archive of planetary experiments, most of them severe, some of them promising, none of them obligated to resemble the one world where human beings first learned to ask the question. Titan and Enceladus sharpen that archive in opposite ways. Titan is broad, atmospheric, landscape-rich, almost novelistic in how fully it stages its strangeness. Enceladus is concentrated, austere, nearly surgical in the way it presents the evidence. Titan says the category of Earth-like process is too narrow. Enceladus says the category of good place to search for life is too narrow. Together, they complete the correction that Jupiter and Europa began. The solar system is no longer just a set of climates under a star. It is a set of internal engines, hidden oceans, displaced chemistries, and stored conditions. The old habitability map is broken. And once that map breaks, the next kind of evidence begins to matter more than surface weather or subsurface chemistry, not because those things stop mattering, but because the solar system now asks a more violent historical question. How much of what we see in planetary architecture is not equilibrium, but injury? Some worlds hide oceans, some worlds hide thresholds, and one giant planet farther out appears to hide a catastrophe so old that it froze into the way the whole world moves. Uranus does not look wounded at first. That may be the strangest part. Uranus looks, at first, like the opposite of drama. No great red storm dominating the telescope image. No bright rings commanding the imagination. No orange haze like Titan. No plume-lit confession like Enceladus. Just a pale blue-green sphere, distant and quiet, with a smoothness that can seem almost evasive. It does not present itself the way Jupiter does, as power, or the way Saturn does, as beauty. Uranus presents itself as understatement, which is one reason it is so easy to underestimate. The planet sits so far from the sun that sunlight there is thin and cold, reduced to a wan brightness that never quite feels intimate with the world it touches. At that distance, even noon would feel like a kind of prolonged twilight compared with Earth. The atmosphere, mostly hydrogen and helium, with methane giving the planet its distinctive color by absorbing red light, reflects a surface calm that is less truth than concealment. Because Uranus is not merely unusual, it is geometrically wrong in a way that suggests ancient violence. Its axis is tilted by about 98 degrees. Not the familiar lean of Earth, where seasons shift because one hemisphere is angled slightly more toward the sun and then the other. Not even the more dramatic tilts of Mars or Saturn. Uranus is effectively rolling around the sun on its side. The poles spend extraordinarily long intervals in sunlight or darkness. Seasons there do not behave like exaggerated Earth seasons. They behave like a system that never returned to intuitive balance. A pole can face the sun for years. Then, years later, turn away into darkness. Day and night at the extreme latitudes become epochal rather than daily. This is not a minor eccentricity. It is a fossilized problem. Because planets do not casually end up this way. A tilt this extreme points toward a deep event in the planet's history, most likely one or more enormous collisions during the formative years of the solar system, when giant impacts were not rare, but constitutive. Some models favor a single titanic impact with a protoplanet roughly twice Earth's mass. Others suggest a sequence of impacts could have produced the present orientation and internal structure. The details remain debated, but the broad implication is difficult to escape. Uranus is not eccentric by temperament. It is eccentric by history. That sentence matters because it enlarges the meaning of planetary architecture once again. Up to now, the solar system has shown us worlds stripped by heat, worlds trapped by atmosphere, worlds drained of habitability, worlds energized by tides, worlds preserving hidden oceans, worlds made beautiful by temporary debris. Uranus adds another category, worlds whose very posture is an injury preserved in motion. The way a planet turns through space can itself be evidence. And posture, in this case, changes everything. The seasons on Uranus are not just a curiosity for astronomy textbooks. They are consequences of a world whose relationship to sunlight has been fundamentally rearranged. For long stretches of its 84 Earth-year orbit, one hemisphere receives far more direct illumination than the other. The atmosphere responds over immense timescales. The circulation patterns, cloud behavior, and thermal balance all play out under a geometry that would feel almost absurd if it did not exist with such composure before our instruments. Uranus is one of the clearest reminders that even the most basic seeming planetary facts, where sunrise falls, how long summer lasts, what upright means, are not universal. They are contingent outcomes of formation history. And yet tilt is only the first layer of the mystery. Because Uranus also appears oddly reluctant to give off internal heat. Jupiter, Saturn, and Neptune all radiate more energy than they receive from the Sun, thanks to residual heat from formation and ongoing internal processes. Uranus is the strange exception among the giant planets. It emits very little excess heat. For decades, that comparative dimness in internal energy has stood as one of the planet's deepest puzzles. Why does Uranus seem so thermally muted? Did whatever event knocked it onto its side also disrupt the transport of heat from its interior? Is the internal structure layered in a way that traps heat unusually effectively? Has the planet simply cooled in a different fashion than its neighbors? We do not yet know with confidence. But again, uncertainty does not weaken the drama. It deepens it. Uranus is not just a tipped giant. It is a tipped giant whose interior may have been altered enough to change the way the whole planet sheds its primordial energy. The wound may not have been cosmetic. It may have changed the metabolism of the world. That possibility gives the planet a strange kind of emotional weight. Jupiter feels active. Saturn feels radiant. Neptune feels dynamically alive. Uranus feels interrupted. Its magnetic field intensifies that feeling. If planetary magnetic fields followed the tidy intuition that a planet's field should emerge more or less centered and aligned with its rotation axis, Uranus would be easier to think about. But it does not. Uranus's magnetic field is both significantly tilted relative to the rotation axis and offset from the planet's center. The result is a magnetosphere with an irregular, lopsided geometry that changes in complex ways as the planet rotates. The field does not sit on Uranus like a stable crown. It behaves more like a displaced engine carried by a body whose orientation was already abnormal. This is one of those cases where the details of planetary physics begin to feel almost anatomical. A giant world thrown sideways, radiating strangely little heat, carrying an off-kilter magnetic structure that turns through a tilted seasonal regime unlike almost anything else in the solar system. It is difficult to look at that combination and still imagine giant planets as interchangeable categories. Uranus resists category by being coherent in its own wrongness. And that wrongness extends outward. Its rings, though far fainter and darker than Saturn's, are themselves part of the planet's severe elegance. Narrow, relatively dark, and less immediately theatrical, they look less like adornment than like evidence. Its moons, too, move within the consequences of the planet's sideways architecture, forming a system that had to accommodate a primary body whose orientation was already radically altered. Even Miranda, one of Uranus's moons, with its bizarre patchwork of terrains, towering cliffs, and signs of catastrophic resurfacing, feels like a local echo of a system marked by disruption. Nothing about Uranus says stable innocence. It says reconstruction. And that is the larger lesson it offers. We tend to imagine planetary systems as if their final forms were the natural flowering of orderly processes. Dust collapses, worlds form, orbits settle. The adults among the planets take their proper places. But Uranus keeps a record of another truth. Order can emerge after violence without ceasing to be the child of violence. A system can look quiet long after the blows that shaped it are over. Regular motion can be the late behavior of objects that were once struck, spun, scattered, and forced into new configurations. The calm comes later. The injury remains. That line could apply to the whole solar system by now, but Uranus makes it almost embarrassingly literal. If Mercury was a wound that never healed, Uranus is a catastrophe that never stopped rotating. It carries the memory of impact, not in a scar you can point to on the surface, but in the way the entire planet moves through sunlight. It is a world whose biography became geometry. There is something especially severe in that, because geometry is harder to romanticize than geology. A crater can be imagined as ancient drama, a cliff can be visualized, a river valley can be mourned. But an axial tilt approaching 98 degrees is colder than that. It is violence abstracted into law, no flames, no visible rupture, just the permanent misalignment of a giant world. And yet, Uranus does not merely enlarge the violence of the solar system's past. It also prepares the mind for a subtler category of discovery, the discovery of worlds not by looking directly at them, but by noticing the disturbances they impose on others. Because Uranus itself once played that role. In the 19th century, after Uranus had joined the known planetary family through telescopic discovery, astronomers began to notice that its observed orbit did not match predictions perfectly. The planet seemed to wander slightly from where Newtonian calculations, based on the known bodies of the solar system, said it should be. This was not enough to overthrow the laws. It was enough to imply that the laws were being acted on by something unseen. That kind of implication matters more than it first appears. A strange world can broaden our imagination. An unseen world discovered through perturbation broadens our epistemology. It changes not just what exists, but how reality becomes visible to science. Because once one planet's motion begins to betray the presence of another, astronomy stops being only the observation of what shines. It becomes the detection of hidden force through consequence. Uranus, in that sense, became a witness against the unseen. And that witness led the solar system to another outer giant, one farther from the sun, colder in light, violent in atmosphere, and conceptually unforgettable for a simple reason. It entered science not as a spot in the sky, but as a solution to a wound in motion. Some worlds announced themselves by appearing. The next one announced itself by refusing to let Uranus move cleanly. That refusal was one of the great turning points in the history of knowing. For most of human experience, a world became real in astronomy the same way it did in ordinary life. It appeared, you saw it, you tracked it. You learned its pattern against the sky. Even when mathematics entered the picture, vision still held the prestige of first contact. A planet was, in some deep intuitive sense, something that gave itself to the eye. Neptune broke that instinct before most people had ever even heard its name. By the early 19th century, Uranus had already expanded the known scale of the solar system, but the more carefully astronomers measured its orbit, the less perfectly it behaved. It did not move wildly. The discrepancy was not dramatic in the theatrical sense. It was subtler than that, and therefore more profound. Uranus kept arriving slightly off script. The deviations were small, but in celestial mechanics, small persistent deviations are not trivial. They are accusations. Something was pulling on the planet from beyond the visible inventory of the solar system. That sentence sounds simple now because science has since made it ordinary for hidden realities to be inferred through effects. Dark matter, black holes, exoplanets detected by transits and wobble. But in the case of Neptune, the logic arrived with almost intolerable elegance. If Newton's laws were right, and the evidence for them was overwhelming, then Uranus's irregularities did not mean the laws had failed. They meant the inventory was incomplete. Somewhere beyond Uranus, another mass was present, unseen but not silent. Its existence was legible in disturbance. Some worlds enter science not by appearing, but by refusing to let other worlds move cleanly. That is one of the most beautiful things ever said by the solar system, because it reveals a universe deeper than visibility. Reality does not need to shine to be found. It only needs to matter enough to leave a trace in motion. In the 1840s, John Couch Adams in England and Urbain Le Verrier in France worked independently on the problem, using the irregularities in Uranus's orbit to predict the location of the unseen planet. There were errors, approximations, missed opportunities, disputes over credit, all the human texture that follows even the most crystalline scientific triumph. But the essential fact remains astonishing. In 1846, after Le Verrier sent his calculations to Johann Galle at the Berlin Observatory, Neptune was found close to the predicted position. Mathematics reached into darkness and pulled out a world. That was not just a discovery of one planet. It was a discovery about how reality can be known. Astronomy ceased, in a deeper sense, to be only the study of luminous objects. It became the study of lawful disturbance. The solar system was now a place where hidden things could be reconstructed from the injuries they imposed on visible order. And when Neptune itself finally comes into focus, it justifies the method. Because Neptune is not a quiet answer to an abstract equation, it is a real world of cold light and violent motion, one of the strangest atmospheres in the solar system. It orbits at an average distance of about 30 astronomical units from the Sun, so far out that sunlight there is reduced to a thin, austere brilliance. Noon on Neptune would not feel like the affirmation of day. It would feel like a distant concession, the Sun. From that world, would no longer dominate the sky as a blazing center. It would seem reduced, though never made harmless by that reduction. And in that blue remoteness, something deeply counterintuitive happens. Neptune has some of the fastest winds in the solar system. This remains one of those facts that resist intuition so completely they become almost philosophical. A world receiving so little solar energy compared with Earth, so far from the Sun, so cold in equilibrium terms, should not feel meteorologically extravagant to the untrained imagination. And yet, cloud systems race through its atmosphere at supersonic speeds. Storms form and evolve. Dark vortices appear and vanish. Methane in the upper atmosphere contributes to the planet's deep blue color, but the visible serenity of that blue hides an atmospheric dynamism severe enough to make Earth's weather feel local and domesticated. This is the same correction the solar system has been forcing on us from the beginning, only translated now into outer darkness. Distance does not mean stillness. Cold does not mean inactivity. Faint sunlight does not guarantee a quiet world. Neptune remains, in many ways, less well understood than the inner planets and the more intensively explored giants. Voyager 2 is still the only spacecraft to have flown past it. In 1989, giving humanity its one direct close look at the planet and its major moon system. What that encounter revealed was enough to secure Neptune's place in this deeper narrative of the solar system. It showed a world with active meteorology, high-altitude methane ice clouds, large storms, and an internal vigor that cannot be explained by solar heating alone. Like Uranus, Neptune is an ice giant rather than a gas giant in the older simplified taxonomy, meaning that beneath its atmosphere lies a deeper composition, richer in heavier volatile substances, water, ammonia, methane in high-pressure states, rather than the overwhelmingly hydrogen-helium dominance of Jupiter and Saturn. But unlike Uranus, Neptune radiates substantial internal heat. The contrast between the two worlds is one of the quiet riddles of giant planet science. Two planets formed in the same general outer regime of the solar system, similar in broad category, yet one is more internally expressive than the other. One lies tipped and thermally muted, the other carries storms and stronger excess heat. The solar system does not merely produce classes of worlds, it produces divergences within classes that keep the science alive. And then there is Triton. If Neptune itself entered knowledge as a gravitational inference made visible, Triton enters the story as a warning that even moon systems cannot always be read as native. Triton orbits Neptune in a retrograde direction, moving opposite to the planet's rotation. That alone is an enormous clue. Large moons that form in place around giant planets are expected to orbit prograde, inheriting the angular momentum of the system that formed them. Triton's backward path strongly suggests capture. It is likely a former Kuiper Belt object, seized by Neptune's gravity long ago. That means Neptune is not merely a planet with moons. It is a planet that stole one. And the theft had consequences. A capture event of that scale would have disrupted any pre-existing moon system, reorganized orbital dynamics, and converted gravitational violence into heat and change. Triton itself is no inert trophy. Voyager 2 revealed a world of nitrogen ice, young surfaces, and active geyser-like plumes, implying geological vitality on a body that should, by older intuition, have long frozen into total passivity. Here again, the outer solar system refuses the category of dead cold storage. Even in remote darkness, worlds can remain active, altered, and internally expressive. Triton also carries a longer future that makes the whole Neptune system feel less settled than it appears, because its orbit is decaying. Over immense timescales, tidal interactions are expected to bring Triton inward until it may eventually be torn apart by Neptune's gravity, perhaps forming a ring system in the distant future. The captured moon is not in stable permanent residence. It is in a very long descent. A world can be discovered through perturbation and still end in dismemberment. That is the kind of sentence the solar system keeps earning. Neptune, then, is not only a historical triumph of calculation, it is a concentration of several of the script's deepest themes: hidden force, misleading appearances, activity where intuition expects stillness, a system shaped not only by original formation, but by capture, disruption, and long futures of decay. Even at the edge of the classical planetary map, the universe refuses to become simple. It remains lawful, yes, but lawfulness is not the same thing as psychological comfort. The laws permit supersonic winds and freezing darkness. They permit moons to be stolen. They permit planets to be found because they disturb their neighbors. None of this flatters the human wish for a tidy cosmos. And that is why Neptune belongs exactly here in the descent. By this point, the solar system has already overturned almost every easy intuition with which it began. The sun is no passive lamp. Mercury is not merely small. Venus is not just bright. Mars is not simply dead. Jupiter is not only giant. Saturn's rings are not permanent. Titan and Enceladus prove that chemistry and hidden oceans can matter more than open skies. Uranus has converted ancient violence into planetary posture. Neptune now adds the epistemological turn. Reality is not limited to what announces itself directly. Sometimes the deepest truths arrive as perturbations first. That shift in how worlds become visible prepares the mind for one final collapse of the old solar system image. Because the next object does not merely challenge a prediction or expand a category, it breaks a definition. It forces science to admit that the old planetary map was not only incomplete, but too psychologically clean. For generations, the solar system could still be imagined as a sequence of planets culminating in a final, lonely outpost. One last world at the edge, dim and distant, but still fitting the grammar of the chart. And then the edge stopped being singular. Then the last planet became the first sign of a population. Then Pluto ceased to be a conclusion and became a crack in the whole idea of a simple solar system. Pluto was supposed to be the far punctuation mark. That was its old role in the human imagination, the small, dim, remote final planet, the lonely endpoint of the solar system, a cold last dot at the edge of the sun's authority, beyond which the story thinned into emptiness. Even people who knew almost nothing else about planetary science often carried that image somewhere in memory. Mercury at the beginning, Pluto at the end, a neat procession from fire to frost, an ordered family with one last quiet child trailing far behind the rest. The image was simple, and the solar system has been punishing simplicity from the beginning. Because Pluto did not become controversial because it stopped mattering. Pluto became controversial because it mattered too much in the wrong way. It forced astronomy to admit that the old planetary story was not just unfinished, it was psychologically convenient. Pluto had been serving as a clean ending for a system that was never actually clean at its edges. Once we began to see those edges properly, the category holding Pluto started to crack. But before that crack, Pluto had already entered science in a way that suited the older map. Its discovery in 1930 by Clyde Tombaugh at Lowell Observatory fit the long-standing desire to find another world beyond Neptune, a Planet X, that would extend the known solar system one step further into darkness. For decades, Pluto held that place, small, faint, hard to characterize, but symbolically stable. It was the final member of the planetary sequence, not because we understood it deeply, but because the chart felt better with an end. That instinct is worth noticing. Human beings do not only seek truth in science, we also seek closure. We like categories that feel complete, inventories that terminate cleanly, maps that appear to know when to stop. Pluto satisfied that appetite for a long time. It made the solar system look narratively elegant. 1 star, 9 planets, a beginning, an end. Even children's mnemonics could hold it in memory without strain. Reality, meanwhile, was preparing an ambush. As observations improved and the outer solar system opened up, Pluto began to look less like an isolated final planet and more like the visible representative of something larger. Its orbit was already odd by the standards of the major planets: eccentric, inclined, and locked in a 3-to-2 resonance with Neptune that prevents the two bodies from colliding, despite Pluto's path crossing Neptune's in projection. That alone hinted that Pluto was not simply another tidy member of the same old planetary class. Its behavior belonged to a different dynamical context. Then the Kuiper Belt emerged into view. This was the decisive shift. Beyond Neptune lay not a single lonely world, but a vast population of icy bodies, remnants of solar system formation, preserved in the cold, moving in a range of resonant and non-resonant orbits. Pluto was not the solitary frontier, after all. It was one object among many members of a broader trans-Neptunian population. And as more of those bodies were discovered, especially ones comparable in scale and complexity, the old question could no longer be avoided. If Pluto is a planet, what do we do with the rest? That is the deeper seriousness behind what many people remember only as the Pluto demotion. It was never just a cultural argument about whether one beloved object deserved respect. It was a taxonomic crisis forced by observation. Science had reached a point where the old category no longer sorted reality cleanly. Either the solar system would gain a swelling inventory of new planets as more large Kuiper Belt objects were found, or the definition of planet would have to narrow. Neither option was emotionally painless, because the discomfort was not really about Pluto. It was about giving up a simple world picture. Pluto was not demoted because it became less interesting. It was demoted because the solar system became larger than the category that held it. That is the line worth keeping. In 2006, the International Astronomical Union formalized the now familiar criteria that placed Pluto in the category of dwarf planet. It orbits the Sun. It is massive enough for self-gravity to pull it into a nearly round shape. But it has not cleared the neighborhood around its orbit in the way the major planets have, meaning it does not dynamically dominate its orbital zone to the same extent. The wording has been debated, criticized, defended, and philosophically unpacked ever since. Scientists still argue, in various ways, about how useful or limiting that classification is depending on context. But whatever one thinks of the exact taxonomy, the conceptual rupture remains. The solar system no longer ends with a lone final planet. It frays into a population. And that fraying matters because it does to the edge of the solar system what Jupiter, Saturn, Titan, and Enceladus did to its interior logic. It removes the old, comforting singularity. Instead of one last object standing at the frontier, we get a region. Instead of closure, we get gradation. Instead of the finality of the 9th planet, we get a field of icy worlds. Resonances, captures, collisions, binaries, migrations, and remnants. The outer solar system ceases to be a clean conclusion. It becomes an archive. Pluto is the first emotionally significant object in that archive. And then New Horizons arrived and made the whole matter impossible to simplify. Before 2015, Pluto's symbolic life greatly exceeded the amount of direct detail we possessed about it. It was distant enough that even powerful telescopes could only show limited information. Many people imagined that whatever Pluto was, it would probably be geologically dull, small, frozen, ancient, a relic more than a world. That expectation lasted until the spacecraft flew past and returned images that changed Pluto from a definitional argument into one of the most vivid planetary places ever seen. Suddenly, Pluto had landscapes. Not generic icy surface landscapes, but startlingly varied terrain, mountains made of water, ice rising like bedrock, because in Pluto's deep cold, water is effectively the structural rock, while nitrogen and other volatiles behave more like mobile substances. Vast plains of nitrogen ice, especially Sputnik Planitia, smooth and bright and cellular in pattern, suggesting active convection in the frozen material, layered haze in the atmosphere, signs of glacial flow, variegated coloration across the surface, a heart-shaped region that popular culture seized on instantly, but which science had to take more seriously as topography, volatile transport, and climatic process. Pluto, in other words, was not a dead pebble. It was a world. That does not undo the taxonomy. It deepens the meaning of the dispute. The reason Pluto remains so emotionally charged is not because sentimentality resists scientific correction. It is because the object itself refuses triviality. Whatever category we place it in, Pluto is geologically and atmospherically richer than many people expected a body of its size and location to be. It keeps the old word planet alive in the mind, not because the definition demands it, but because the experience of seeing it does. The solar system does not make the emotional boundary between planet and non-planet easy to maintain. And Pluto's relationship with Charon intensifies that feeling. Charon is so large relative to Pluto that the pair are often described as a binary or double system in a practical dynamical sense. They do not behave like a giant planet with a tiny moon. They orbit a shared barycenter located outside Pluto itself. This is another small but profound insult to the old classroom model of the solar system. Even the supposedly simple planet with moon pattern becomes less stable at the edge. Categories blur, centers shift, the architecture loosens. The farther out we go, the less the solar system resembles the diagram that first taught us its existence. That is why Pluto belongs where it does in this descent, not as an afterthought, not as nostalgia, as a structural necessity. Mercury dismantled the idea that sunlight is gentle. Venus dismantled the idea that Earth-like size means Earth-like fate. Mars dismantled the idea that habitability, once achieved, remains secure. Jupiter and Saturn dismantled the idea that visible surfaces and static beauty are the core of planetary meaning. Titan and Enceladus dismantled the idea that open skies matter most for chemistry and possible life. Uranus dismantled the idea that calm geometry implies peaceful history. Neptune dismantled the idea that the unseen cannot be known. Pluto dismantles the last tidy illusion that the solar system has a clean outer edge. It does not. It opens into a domain of leftovers, migrants, survivors, and unincorporated bodies, objects that never became major planets, objects displaced by giant planet migration, objects preserving the chemistry and memory of the early solar system in deep cold. The Kuiper Belt is not an appendix. It is part of the story of origin. Pluto matters because it made us look there seriously. And once we did, the old ending could not survive. That is the real force of the Pluto episode. The science was not simply reclassifying one object. It was acknowledging that our psychological need for clean categories had lagged behind the evidence. Pluto became the site where culture met a painful scientific maturity. The world is not organized to preserve our mnemonics. The universe is not required to make its boundaries obvious or its classes emotionally satisfying. Sometimes the most honest thing science can do is admit that a beloved label concealed a deeper structure. And yet Pluto is not merely a lesson in humility. It is also a lesson in abundance. Because once the edge of the solar system stops being singular, it becomes fertile in meaning. Now, Pluto can be seen not as a diminished planet, but as a gateway object into a wider trans-Neptunian population, one with implications for planetary formation, migration, collision history, volatile evolution, and the inventory of early solar system material. The outer darkness is no longer empty. It is populated. The silence beyond Neptune contains not a final ornament, but a record of what never finished forming, a record of what survived displacement, a record of what the young solar system left behind. That phrase, left behind, should sound familiar by now. The whole solar system is increasingly starting to feel like a layered forensic scene. The planets are not just worlds, they are outcomes. The moons are not just companions. They are experiments in energy and chemistry. The rings are not just adornment. They are temporary debris. And Pluto is not just a reclassified object. It is evidence that the solar system did not harden into its present form through clean completion. It retained an outer memory of unfinishedness. That memory points backward. Because once Pluto cracks the simple outer map, the next question no longer concerns classification. It concerns origin at the largest level. What kind of system makes this many different outcomes at once? What kind of early history produces stripped cores, runaway greenhouse worlds, dead habitable worlds, tidal ocean moons, temporary ring systems, tipped giants, captured moons, and a trans-Neptunian archive of leftovers at the edge? At that point, the solar system stops looking like a collection. It starts looking like the residue of a negotiation so violent and so intricate that the order we see now is only the cooled surface of it. That cooled surface is what misleads us. When we look at the solar system as it exists now, we inherit the final arrangement and instinctively treat it as the intended one. The planets orbit where they orbit. The moons accompany them. The asteroid belt sits between Mars and Jupiter like a natural divider. The Kuiper belt drifts beyond Neptune. Everything appears to occupy its proper place, even after all the damage, strangeness, and hidden interiors we have already passed through. The larger architecture can still tempt the mind into one last illusion, that this was always the shape waiting to emerge. It was not. The present solar system is not a blueprint made visible. It is a negotiated outcome. What we call order is the residue left after an era when almost nothing about the arrangement was settled. To grasp that honestly, you have to return to a time before there were planets in the emotional sense at all, before worlds had names, before surfaces existed, before atmospheres could trap heat or lose it, before oceans could lie open to the sky or hide under ice. There was a young sun, still forming, surrounded by a rotating disk of gas and dust, a protoplanetary disk made from the same collapsing cloud that gave birth to the star itself. This is where the solar system begins in any meaningful physical sense, not with finished spheres, with particulate matter in motion, with gradients, with collision, with heat, with sorting. It is difficult to picture because our intuition wants beginnings to feel clean. But planetary beginnings are not clean. They are abrasive. Tiny grains collide and stick. Larger aggregates grow. Some shatter, some merge. Relative velocities matter. Composition matters. Distance from the sun matters because temperature determines which materials can condense and remain stable. Close to the young sun, only refractory materials, metals and rocky silicates, persist comfortably. Farther out, beyond what planetary scientists call frost lines or snow lines, volatile compounds like water ice can remain solid, dramatically increasing the amount of material available for growth. The disk is not one uniform nursery. It is a thermodynamic sorting field. And the consequences of that sorting run through everything we now see. The inner planets are rocky, not because rock is somehow the default substance of worlds, but because the early inner solar system was too hot for abundant volatile-rich solids to remain stable in the same way. The outer system could build giant cores more efficiently because ice has added mass and opportunity. Chemistry became geography. Temperature became destiny long before any world had a climate. This is one reason planetary science feels so severe when it is done honestly. The things we later experience as beautiful or tragic are often rooted in conditions established before the worlds themselves existed in anything like their final form. Mercury's metallic extremity, Venus's atmospheric catastrophe, Earth's contingent balance, Mars's insufficient retention, the giant planet's bulk, the ocean moon's icy shells. All of these later biographies begin as possibilities constrained by where in the disk a body grew. What material was available there, how quickly accretion happened, what collisions followed, and how the larger system kept changing around it. Because the disk did not merely produce worlds, it kept disturbing them as they formed. This is where the young solar system becomes much harder to love in the naive way. Accretion sounds gentle in language, matter gathering, worlds assembling, but the actual process includes impacts large enough to melt surfaces, differentiate interiors, vaporize crusts, and reset trajectories. planetesimals become protoplanets through repeated violence. Some bodies win mass, some lose it. Some are incorporated. Some are shattered into debris. Some are thrown inward, some outward. A forming planet is not a calm accumulation. It is a body struggling to remain itself while the system keeps revising the terms. The Earth-Moon system is one of the clearest surviving witnesses to this. The leading model for the Moon's origin involves a giant impact between the young Earth and a Mars-sized body, often called Theia. The collision was not a decorative event in Earth's past. It was formative. It helped define the Earth we now treat as baseline reality. A major fraction of the early planet's outer layers was ejected, reprocessed, and eventually reassembled into the Moon. So, even our most intimate celestial companion is not an accessory. It is a scar-turned-satellite. Home itself was collision-built. That sentence should change the emotional register of the whole solar system. Because once you admit that Earth required catastrophic restructuring during its formation, the other worlds stop looking like deviations from a peaceful norm and start looking like parallel outcomes of a common brutality. Mercury may indeed be the remnant of stripping. Uranus may carry its ancient blow in axial form. The asteroid belt may preserve the fact that not every region was allowed to consolidate into a planet, with Jupiter's gravity helping prevent that zone from settling into a single dominant world. The system is full of bodies whose final form was not what a quiet accretion story alone would have produced. And then the giant planets complicate things further. For a long time, it was natural to imagine that the planets more or less formed where they now reside. But both our own solar system and the discovery of exoplanets have made that picture much less comfortable. Migration, planetary movement through the disk, or later dynamical evolution, is no longer an exotic possibility. It is a central concept. Giant planets can shift their orbits, especially during the early history of a system, altering the trajectories of smaller bodies, scattering material, capturing resonances, and reorganizing the architecture of the whole planetary family. In our solar system, models such as the NICE model and related migration scenarios suggest that the outer planets may not have always occupied their present arrangement. Their gravitational interactions with residual planetesimal populations could have driven orbital shifts, scattering countless smaller bodies inward and outward. Such rearrangements may help explain aspects of the Kuiper Belt. The populations of Trojan asteroids, irregular moons, and periods of intense bombardment in the inner solar system. Not every detail is settled. Not every timing issue is fully closed. But the broad lesson is unavoidable. The giant planets may have moved, and when giants move, smaller worlds inherit the consequences. This is the moment where the solar system stops resembling a family portrait and starts resembling a political history. Mass negotiates, gravity bargains. Some bodies are expelled from the center. Some are delivered inward. Some are trapped in resonances that preserve their orbits for billions of years. Some are broken. Some are protected only because other things are destroyed first. Even stability in the mature solar system often turns out to be the long-term outcome of earlier instability working itself toward a temporary ceasefire. The asteroid belt is a perfect example of how misleading appearance can be here. In school diagrams, it often appears as a thick crowd of rocks packed tightly between Mars and Jupiter, almost like a barrier. In reality, the belt is mostly empty space, but the bodies within it, from dust to dwarf planet Ceres, preserve the fact that this region did not become a full planet. Why? Because Jupiter's gravitational influence stirred the zone, increasing collision speeds and frustrating simple accretion into one dominant body. The belt is not just leftover material. It is leftover material left over for a reason. A failed planet is often not a thing. It is a region. That line matters because it expands failure from biography to architecture. Worlds do not merely fail individually. Entire parts of a system can be prevented from becoming what simpler stories once implied they should have become. The solar system contains not only finished bodies and damaged bodies, but interrupted zones. An interruption may have been essential to us. The late delivery of volatile-rich material to the inner solar system, water, and other compounds brought by certain classes of asteroids. Possibly comets in more limited roles depending on isotopic constraints, remains one of the great formation questions tied directly to Earth's history. Again, caution matters. The exact proportions, source populations, and timing are still active areas of research, but it is very likely that Earth's inventory of water and other volatiles was shaped not just by local formation, but by redistribution. Material moved, impactors delivered chemistry. The inner planets were not closed systems receiving only their birth allotments. They were participating in a larger traffic of matter. Earth's oceans may owe part of their existence to a solar system that refused to keep materials in neat places. That is not a poetic flourish. It is a planetary fact with emotional force. Because it means that habitability may have depended not on local perfection, but on the right kind of disorder, too orderly, and the inner planets stay dry and chemically impoverished, too violent, and the same worlds may never stabilize enough to hold air and water long term. The path to a habitable Earth may have required precisely the sort of giant planet stirring and impact delivery that also made the young solar system so dangerous. The forces that threatened emerging worlds may also have provisioned them. This is the deeper law that has been hiding under every world in the script so far. The solar system was not assembled. It was negotiated through impact, heat, theft, and time. That sentence is not dramatic decoration. It is structural truth. Impact, because collisions built, stripped, melted, reset, and in some cases, destroyed. Heat, because thermal gradients in the young disk sorted materials, and because internal and radiogenic heat shaped evolving interiors. Theft, because capture, scattering, migration, and redistribution moved matter across the system in ways no static blueprint would predict. Time, because none of this happened at once, and because planetary identity is what remains after billions of years of selection. Once you see the system that way, the present arrangement looks less like a natural picture and more like a legal settlement whose documents have been shredded, leaving only the surviving bodies as witnesses. Mercury testifies to stripping, Venus to climatic thresholds, Mars to attrition, Jupiter to system-scale force, the ocean moons to hidden persistence, Saturn's rings to temporary structures, Uranus to catastrophic reorientation, Neptune to perturbative truth, Pluto to unfinishedness at the edge. The solar system is full of testimony. What formation theory does is give those testimonies a common courtroom. And that courtroom is still active. We do not have every answer. Important parts of early solar system history remain under debate. The exact timing and severity of bombardment episodes, the detailed migration histories of the outer planets, the full source inventory for Earth's volatiles, the specific impact histories that yielded certain current planetary structures. But this incompleteness should not be mistaken for vagueness. The overall picture is already severe enough. The worlds nearest us are not the natural expressions of a polite cosmic order. They are survivors and products of a prolonged sorting process in which most possible outcomes were never guaranteed to last. That realization points to the last hard question. If the solar system produced so many partial worlds, failed worlds, hidden worlds, overheated worlds, underprotected worlds, stolen moons, temporary structures, and unfinished edges, then why did one world remain open long enough for chemistry to become memory? Memory to become thought, and thought to look back across the system that made it? Why this balance here? Why did so many neighboring possibilities collapse into too much, too little, too early, too deep, too cold, too exposed, or too unstable, while Earth remained habitable long enough to become conscious of the alternatives? That is where the story becomes least comfortable of all, because the answer, whatever its details, does not flatter us. It does not say Earth was the intended center. It says Earth was the narrow case that held. Held is the important word. Not chosen, not designed, not guaranteed. Held. By the time you reach this point in the solar system story, the old instinct to treat Earth as the normal case has become almost impossible to defend. Normal compared with what? Compared with Mercury. nearly stripped to its metallic severity? With Venus, where atmosphere became sentence rather than shelter. With Mars, which appears to have crossed out of habitability by increments too patient to be dramatic. With Europa and Enceladus, where water may survive only by retreating beneath ice. With Titan, where climate exists but in chemistries almost nothing terrestrial could tolerate. With Uranus, still carrying catastrophe in its posture. With Pluto, a survivor at the edge of a system that never finished becoming simple. Once you have seen the alternatives, Earth stops looking like the template. It starts looking like the narrow case that stayed open. And staying open is harder than it sounds. That is one of the deepest corrections planetary science forces on us. We often talk about habitability as though it were a single achievement. Get the right distance from the star, keep some water, maintain an atmosphere, and the rest follows. But real habitability is not a switch. It is a choreography. Multiple conditions must persist together across immense stretches of time. Not perfectly, but well enough. The world has to avoid too much and too little at once. Too much greenhouse trapping and the surface hardens into furnace. Too little atmospheric retention and liquid water becomes unstable. Too little magnetic protection at the wrong stage and stripping pressure grows more severe. Too little internal activity and the cycles that help regulate long-term surface conditions may falter. Too much bombardment for too long and continuity keeps breaking. Too little chemical delivery and the ingredients arrive impoverished. Too much orbital chaos and the climate never stays within useful bounds. Too much stillness, meanwhile, can be its own failure if a planet cannot recycle what life and geology require. Earth did not solve one problem. It survived a stack of them. That survival begins with location, but does not end there. Yes, Earth orbits in the region around the Sun where liquid water can persist at the surface under the right atmospheric conditions. That matters, but the phrase habitable zone becomes misleading when treated like a magic circle. Venus is a warning against simplistic use of that idea, and Mars is another. Distance from the Sun provides a thermal context. It does not guarantee the planetary response. A world still needs enough atmosphere, but not too much. The right chemistry, but not locked into catastrophic feedback. A climate system capable of absorbing disturbances without permanently crossing the wrong threshold. The habitable zone is not a verdict. It is an opportunity. Earth was not just in range. It answered correctly for a very long time. The atmosphere is one of those answers, thick enough to sustain pressure, climate, and surface liquid water, but not so thick in greenhouse composition that the system tipped into Venusian fate. Nitrogen dominant, oxygen abundant only later through biology, carbon dioxide present but modest, water cycling between surface, air, ice, and rock. None of this should be treated as static. Earth's atmosphere has changed dramatically across deep time, and life itself transformed it. But that is precisely the point. The atmosphere was not a fixed gift. It was part of a dynamic planetary system able to evolve without collapsing into uninhabitability. The magnetic field is another answer. Again, this should be handled carefully. A magnetic field is not the sole determinant of atmospheric survival, and the comparative science is subtler than simplistic popular summaries often suggest. Venus lacks a global intrinsic magnetic field, yet still retains a massive atmosphere. Mars lost its global dynamo and suffered substantial atmospheric loss, but that alone is not the entire story. Still, Earth's magnetosphere matters. It moderates the interaction with the solar wind, helps protect the atmosphere over geological time, and reduces surface radiation exposure in ways deeply favorable to long-term biological stability. The field does not create habitability by itself. It helps preserve a habitable arrangement. Then there is plate tectonics, or at least long-term geodynamic cycling. Here the science deserves both seriousness and restraint. Earth is the only world we currently know to exhibit active plate tectonics in the modern style, and that fact may be central to the planet's long-term climate regulation. Through processes involving volcanism, weathering, subduction, and the carbon silicate cycle, Earth possesses mechanisms that can buffer carbon dioxide on immense timescales. pulling it out of the atmosphere under some conditions and returning it under others. These are not perfect controls. Earth has endured severe climate shifts, glaciations, extinctions, and episodes of profound upheaval, but the broader system has remained flexible enough to avoid the terminal traps visible elsewhere in the solar system. The geology stayed involved. A habitable world may need not just water and air, but a deep interior willing to keep participating. That may be one of Earth's least intuitive advantages. We tend to think life happens at the surface and therefore judge worlds by surface appearance. But again and again, the solar system has taught us that interiors matter. On Earth, the interior helped generate a magnetic field, drove volcanism, sustained tectonic recycling, and shaped the chemical and atmospheric conditions under which surface life could persist. Earth's habitability was never only skin deep. It was interior enabled. The moon may belong to this answer as well. Not in the simplistic sense that without the moon, life is impossible. Science does not support that kind of theatrical certainty. But the moon's influence on Earth is real and substantial. It stabilizes Earth's axial tilt against some long-term chaotic variations, helping moderate climate swings over geological timescales. It drives tides, which may have mattered in early coastal or chemical environments. It is the outcome of a giant impact that also reshaped Earth's early thermal and compositional history. Even here, our planetary stability may be partly the late effect of earlier violence. Home was not protected from catastrophe. Home was, in part, built by one. This is why the word held feels truer than any warmer alternative. Earth did not stand outside the solar system's brutality. It held together through it. That matters because it dissolves another comforting illusion, the illusion that life appeared because Earth was always gentle. Earth was never always gentle. The early planet was bombarded, volcanically intense, chemically unstable by any ordinary human standard. Oceans may have formed early, been disrupted, persisted, and evolved under conditions no human being would call calm. Life itself likely emerged into a world far stranger than the one we inherit now. And even later, after biology had gained immense continuity, Earth still passed through mass extinctions, asteroid impacts, supervolcanic episodes, global glaciations, atmospheric transformations, tectonic reorganizations, and shifting continental arrangements. Habitability did not mean comfort, it meant recoverability. That distinction may be one of the most important in the entire story. A planet does not need to be benign at all times. It needs to avoid becoming terminally hostile. It needs to sustain windows, cycles, and recoveries long enough for complexity to deepen. Earth has been violent and still habitable. Mars may once have been clement and still lost the balance. Venus may once have been less hostile and still crossed the wrong threshold. Recoverability, planetary resilience without permanence, is closer to the truth of Earth than any static image of paradise. And once you say that, Earth's uniqueness becomes at once smaller and more precious. Smaller because it is no longer a sacred exception in a mystical sense. The laws that shaped Earth also shaped every failed or hidden world around it. Nothing about our planet required a suspension of physics. Earth is not miraculous in the sense of being beyond rule. It is miraculous in the older, harder sense of being lawful and still improbable in its exact continuity. More precious, because the alternatives are now visible. We can point to them. Too hot, too thin, too buried, too stripped, too unstable, too unfinished. The solar system surrounds Earth with counterfactuals. That is what gives comparative planetology its emotional force. It turns neighboring worlds into explicit demonstrations of what did not hold. You do not have to imagine in the abstract what happens when a rocky planet runs away thermally, or loses too much atmosphere, or hides its water below miles of ice, or becomes dynamically interrupted. The system has already built those examples for you. Earth does not look normal once you have seen the alternatives. That sentence is where the philosophical pressure of the whole script tightens. Because if Earth is not normal, then the human tendency to treat our own conditions as baseline reality begins to look like a local superstition. Breathable air is not baseline. Open oceans are not baseline. Blue sky is not baseline. Long-term surface liquid water is not baseline. A magnetic field, tectonically active crust, moderate greenhouse balance, stable enough orbital history, and billions of years of continuity under an evolving star. None of these are baseline. They are a rare conjunction within this system, and perhaps not infinitely common beyond it either. That does not mean Earth is unique in the universe. Science cannot responsibly leap that far. Exoplanet studies have already shown that planetary diversity across the galaxy is enormous, and many rocky planets exist in star systems beyond our own. Some may prove clement, some may host conditions favorable to life, some may be stranger than anything here. The lesson is not cosmic loneliness masquerading as certainty. The lesson is narrower and more rigorous. Within the solar system, Earth is not the default expression of what planets do. It is one successful arrangement among many unsuccessful, interrupted, hidden, or transformed arrangements. The distinction matters because it rescues awe from vanity. If Earth were the center by design, our gratitude would be less intelligent. If the solar system were arranged for us, wonder would become self-flattery. But that is not what the evidence says. The evidence says something harder, and, in the end, more beautiful. The same laws that made Mercury severe, Venus terminally trapped, Mars dwindled, Europa buried, Titan alien, Uranus wounded, and Pluto unfinished also made Earth habitable enough for mind. The universe did not suspend its indifference to produce us. It produced a lawful range of outcomes, and one of them stayed open long enough for consciousness to emerge. That is not comfort. It is haunting clarity, because it means our home is real in the fullest possible sense, not guaranteed, not idealized, not eternal, but contingent and therefore legible. Earth can now be seen not as the obvious center of a friendly neighborhood, but as a temporary answer within a much larger planetary experiment. The oceans, the air, the long continuity of life, the fragile extension of civilization beneath a star that can still remind us of its power. None of this is the natural state of matter. It is one arrangement that endured, and endured under a deadline. The sun will continue to evolve. Earth's long-term habitability is not infinite. On astronomical timescales, the same stellar relationship that made life possible will eventually close the window, long before the sun becomes a red giant. Increasing solar luminosity will alter Earth's climate in ways that move the planet beyond the conditions complex life now depends on. Even our success is temporary. The narrow case that held does not hold forever. That is the final emotional discipline the solar system asks of us. Do not confuse duration with permanence. Do not confuse rarity with entitlement. Do not confuse habitability with promise. Earth has been astonishingly durable on human and biological timescales, but durability is not exemption. We live on a world that remained open, not on a world that was ever owed to remain so. And once you understand that, the meaning of home changes. Home is no longer the center from which the rest of the solar system looks strange. Home becomes the one place whose strangeness we had normalized because we were born inside it. The last illusion is almost gone now. The heavens were never arranged around us. The planets were never waiting to become a lesson. The solar system was never a stable stage on which Earth simply happened to appear. It was a sorting process, a sequence of thresholds, a system of violent negotiations out of which one world remained permeable enough for life to deepen, thought to emerge, and history to begin. Which means the real secret of the solar system is no longer sitting inside any one planet, moon, ring, or orbit. It is sitting inside the comparison itself. Inside the fact that when you finally read the whole system together, Earth stops looking central. It starts looking brief, contingent, and impossibly dear. That feeling is the adult form of awe. Not the first kind, not the easy kind, not the kind that comes from saying the solar system is vast, beautiful, mysterious, and leaving the words undisturbed. The adult form of awe begins later, after the comparisons have done their work, after beauty has been forced to share the room with threshold, catastrophe, attrition, hidden interiors, stolen moons, temporary rings, and unfinished edges. After you have looked long enough to understand that What surrounds Earth is not a decorative neighborhood of curiosities, but a set of explicit planetary counter-arguments. At that point, the question changes. It is no longer, what strange things are out there? It becomes, what exactly had to remain true here, and for how long, for any of this to happen at all? That is the mature version of the mystery. Because once Earth stops being treated as the default, habitability stops being a backdrop and becomes a structure that must be explained, not explained away in one slogan, not reduced to the right distance from the sun. Explained as a layered endurance problem inside a solar system that seems almost perversely efficient at producing other outcomes. A rocky world can remain too close and be stripped towards severity. It can keep its air and still harden into a greenhouse prison. It can begin with water and later fail to protect the conditions that keep water useful at the surface. It can hide oceans, but only under miles of ice and in permanent darkness. It can preserve climate-like processes and chemistries human life cannot use. It can be knocked sideways. It can become the remnant of a population rather than the conclusion of a sequence. This is why the phrase Earth-like should always sound provisional. Not false, just dangerously incomplete. Earth-like in mass, in radius, in bulk composition, in orbital distance, in atmospheric chemistry, in geodynamic behavior, in magnetospheric protection, in long-term climate cycling, in biological history. The solar system itself has already taught us that partial resemblance is easy. Sustained convergence is rare. Many worlds can share one or two vital features. Very few appear to share the full stack. And that full stack is where the real difficulty lives. Earth is not habitable because it won one lottery. Earth is habitable because it kept surviving multiple draws. A useful amount of sunlight, but not a terminal amount. An atmosphere thick enough, but not crushingly so. Water able to remain liquid at the surface across deep time. A planetary mass sufficient to retain what needed retaining. Interior processes that did not go silent too soon. Climate feedbacks that buffered more than they destroyed. A history violent enough to deliver materials and shape the system. But not so violent for too long. That continuity never took hold. A star stable enough for biology, but active enough to remind every orbiting world that safety was conditional. If you describe those conditions one by one, they can sound almost administrative. A checklist, a set of knobs turned to workable values. But that is only because language can make contingency feel flatter than it is. In reality, what you are describing is a world remaining inside a narrow corridor while nearby examples visibly strike the walls. Venus tells you what happens when atmospheric and thermal feedback move too far in one direction. Mars tells you what happens when retention and internal longevity move too far in another. Europa and Enceladus tell you that water can survive without surface freedom. Titan tells you that climate can exist without terrestrial chemistry. Mercury tells you what exposure does when there is almost nothing left to soften it. Earth is not meaningful because it is perfect. It is meaningful because it is bracketed. That may be the hardest truth in the whole script, because bracketing removes every trace of cosmic flattery while leaving wonder intact. The old human temptation was to read the heavens anthropocentrically. The lights above exist for us. The earth below is central by intention. The rest is ornament or backdrop. Science dismantled that vision gradually, then decisively. Copernicus displaced the Earth geometrically. Darwin displaced us biologically. Modern cosmology displaced us in scale, and comparative planetology has now begun displacing us environmentally. We are not standing at the universal center of what worlds naturally do. We are standing in one of the narrow local states where worlds remained open long enough for organisms to ask what worlds naturally do. That is very different, and more severe, because it means the true significance of Earth does not come from rank. It comes from duration under pressure. It is the significance of a bridge still standing after every neighboring design failure has become visible. Not the only possible bridge in the universe. Perhaps. Science is not entitled to make that claim. But in this solar system, the bridge we know is real, and the alternative designs are no longer hypothetical. We have seen them. We have names for them. That is why a mature encounter with the solar system changes the emotional meaning of even ordinary terrestrial things. A blue sky stops feeling generic. It becomes a rare atmospheric answer. Ocean water stops feeling like scenery. It becomes the visible expression of a planetary balance that could have been otherwise. Even weather becomes newly legible, not just as local inconvenience or beauty, but as the surface signature of a deep system still functioning. Tides, clouds, rainfall, a breathable pressure range, seasons that vary without breaking habitability. None of these are trivial once you have looked carefully at the alternatives. They are the visible face of a world still holding. And once you say still, time enters again. This is essential because habitability only acquires its full seriousness when you stop treating it as a state and start treating it as an interval. Earth's success is not merely that it became habitable, it is that it stayed habitable long enough for complexity to deepen through multiple layers: abiotic chemistry, microbial life, ecosystems, multicellularity, intelligence, civilization, memory, science. Each layer required not perfection, but continuity. Enough continuity that total reset did not win. Enough continuity that adaptation outran extinction, often enough to build history instead of erasing it back to chemistry every time. This is what neighboring worlds sharpen into focus. Mars may have had environments where life could have emerged, but did those environments persist with enough depth and breadth? Venus may once have had milder conditions, but did the climate remain within a survivable corridor long enough? Europa or Enceladus may have oceans and energy, but how do buried oceans under ice compare in continuity and complexity? With open planetary surfaces over billions of years, Titan may stage astonishing chemistry, but can prebiotic possibility become something more under that regime, or does it remain perpetually preparatory? We do not know all those answers. Scientific honesty requires that we do not pretend to, but the fact that the questions even take that form tells you how far the narrative has shifted. The solar system is no longer a set of objects ordered by distance from the sun. It is a comparative laboratory of planetary persistence. And persistence is not equally distributed. Some worlds burn, some worlds fade, some worlds hide, some worlds never finish. One world, here, remain traversable enough for memory to accumulate. That accumulation may be the deepest planetary miracle that science can discuss without ceasing to be science. Not miracle as violation, miracle as lawful improbability experienced from within. Matter organized itself into a biosphere on a rocky world orbiting an ordinary star, within a solar system full of evidence that the same laws often lead elsewhere. Then that biosphere changed the atmosphere, the chemistry, the surface, and eventually produced a species capable of reading the neighboring failures and realizing, late and imperfectly, what had been true the whole time. The point is not that Earth was secretly destined. The point is that destiny is the wrong category. The solar system does not speak in the language of destiny. It speaks in thresholds, feedbacks, dynamics, persistence, and loss. Once you learn that language, every world becomes more legible and less consoling. Venus is not cursed, it is lawful. Mars is not tragic in a literary sense. It is lawful. Europa's buried ocean, Titan's methane weather, Saturn's draining rings, Uranus's sideways year, Neptune's inferred existence, Pluto's fracture of the clean outer edge, lawful, all of it. The laws are stable. The outcomes are not psychologically kind. And that may be exactly why the final perception shift matters so much. Because it rescues wonder from fantasy. Fantasy says the universe is meaningful because it was arranged around us. Science says the universe is meaningful because lawful reality, followed honestly, becomes stranger, colder, more contingent, and more beautiful than self-flattery ever allowed. The solar system is the nearest proof of that. It is close enough to study in detail, old enough to preserve deep history, diverse enough to expose multiple planetary outcomes, and intimate enough that its lessons fall directly back onto Earth. We do not need to leave the solar system to discover that intuition is provincial. We do not need interstellar travel to learn that visible surfaces are often not fundamental. We do not need speculative alien civilizations to feel the scale of planetary contingency. Our own neighborhood is already sufficient. It already contains the argument. The evidence has been circling overhead all along. And the argument is now difficult to avoid. Earth is not the center in any privileged cosmic sense. Earth is not the generic form of a habitable world. Earth is not the expected output of rocky planet formation. Earth is not permanently safe. Earth is the narrow case that stayed open long enough for us to mistake it for normal. Once that settles in, the remaining move of the script is no longer explanatory. It is almost moral, though not in the sermonizing sense, more like an adjustment of posture, because if home is not the default state of matter, then home acquires a density of meaning that no sentimental rhetoric can improve. It becomes harder to trivialize, harder to assume away, harder to place beneath our notice while we go about our lives as though the atmosphere, oceans, magnetosphere, and climatic balance were mere scenery. They are not scenery. They are the local form of a rarity. And rarity is not just a reason for gratitude. It is a reason for precision, for intellectual seriousness, for refusing both despair and vanity. Despair would misunderstand the achievement. Vanity would misunderstand the cause. The achievement is that a lawful universe, indifferent to comfort, produced at least one world in this system where complexity held. The cause is not that the universe needed us. It is that the balance remained open long enough. That is what the neighboring worlds have been trying to teach us this whole time. They are not merely strange because they are far away. They are instructive because they are near enough to compare. They are the visible forms of everything Earth did not become. And once you understand that, the last step is inevitable. The greatest secret of the solar system is not hidden under the clouds of Venus, beneath the ice of Europa, in the storms of Jupiter, or out beyond Pluto among the frozen remnants. It is hidden in the comparison that makes Earth legible at last. The comparison that turns our own world from background into evidence. Evidence of what exactly? Not that the solar system was made for us, not that Earth was placed carefully in a celestial cradle while every other world was assigned a dramatic but secondary role. Not that the universe, after all its violence, secretly intended one blue planet to become the point of the story. The evidence points somewhere harder than that. It points to a system that never promised us anything. That is the final correction, the one all the earlier revelations have been preparing. The sun was never a benevolent lamp. It was an active star whose stability was real, but conditional in all the ways that matter. The planets were never a tidy family of variations on one successful design. They were divergent outcomes of the same laws working under different constraints. The moons were never mere accessories. Some became hidden oceans. Some became laboratories of strange chemistry. Some were captured. Some were broken. The rings were never symbols of permanence. They were matter temporarily prevented from becoming something simpler. Even the outer edge was never a clean ending. It was the beginning of a population. And Earth was never the standard by which the rest should be measured. Earth was the exception we began inside. That difference changes everything. Because once you stop treating home as the baseline, the whole solar system rearranges itself in the mind. Mercury is no longer just the scorched innermost planet. It is the record of what happens when a rocky world survives by becoming almost all core. Venus is no longer just Earth's twin. It is the nearest demonstration that a habitable-looking possibility can become a planetary trap. Mars is no longer simply the dream of another home. It is the memory of one that may have come close and then narrowed away. Europa, Enceladus, and Titan are no longer exotic side notes. They are warnings that life's conditions may hide where our instincts never first look. Uranus is a catastrophe frozen into elegance. Neptune is a proof that invisible realities can be found by the wounds they leave in motion. Pluto is the object that broke the illusion of a neatly finished map. Taken one by one, these worlds are extraordinary. Read together, they become something else. They become a set of neighboring refusals of every easy intuition we brought to the heavens. Refusals of the idea that visible surfaces are fundamental. Refusals of the idea that sunlight alone defines possibility. Refusals of the idea that beauty implies stability. That size implies importance. That atmosphere implies safety. That distance implies stillness. That categories will remain clean once evidence deepens. By the end, the solar system has not simply shown us many strange things. It has dismantled the mental architecture that once made Earth feel like the obvious form of planetary reality. That dismantling is the secret, not hidden in one crater or one ocean or one storm, but in the pattern they make together. The biggest secrets of our solar system are not really secrets of objects. They are secrets of comparison. Comparison is what makes reality sharpen. A single world can be admired. Several worlds, honestly read beside one another, become an argument. They let you see that Earth's oceans are not inevitable because Mars once had water and lost the conditions that kept it useful. They let you see that an atmosphere is not automatically a gift because Venus turned one into a machine for trapping ruin. They let you see that buried water may outlast surface water because the icy moons kept oceans by hiding them. They let you see that giant planets do not merely decorate the outer system because Jupiter and Saturn shape the fates of smaller bodies and perhaps the inventory of worlds like ours. They let you see that the outskirts are not empty because Pluto opened onto a whole archive of unfinishedness beyond Neptune. Only then does Earth come fully into focus. Not as the center, as the narrow bridge, a world that held onto air without turning that air into a prison, a world that held onto water at the surface without freezing it away or burying it forever, a world with enough mass, enough chemistry, enough internal activity, enough shielding, enough continuity, a world that endured bombardment without being permanently closed by it, a world whose climate remained unstable enough to be dynamic, but not so unstable that it lost the long thread required for complexity, a world where life did not merely begin, but kept going. That is the part the neighboring planets illuminate with almost painful clarity. Life does not just need a beginning. It needs a duration. A planet can flirt with habitability and still fail to keep the window open. It can host water briefly, chemistry briefly, clement conditions briefly, but for matter to become cells, and cells to become ecosystems, and ecosystems to become deep time, and deep time to become memory, language, and science. The world cannot merely visit the right state. It has to remain traversable enough for history to accumulate. Earth did that. Not because history was owed to it, because the balance held. For a while. That phrase matters more than ever at the end. For a while? Because one of the last consolations the solar system removes is the fantasy of permanence. Earth's success is real. Its habitability is real. Its long biological continuity is real. But none of that is eternal. The sun will brighten. The climate envelope that complex life depends on will eventually close. Long before the sun swells into a red giant, the favorable interval we experience as normal will end. Even our world's extraordinary endurance is a temporal condition, not a cosmic entitlement. This should not flatten wonder into sadness. It should refine wonder into honesty. The adult emotional residue of the solar system is not despair. It is not triumph. It is something colder and more exacting than either. A recognition that reality can be lawful without being arranged for us, indifferent without being meaningless, severe without being empty of beauty. In fact, the beauty becomes stronger once self-flattery is removed. A universe that needed us would be smaller than this one. A solar system built to reassure us would be less astonishing than the one we actually inhabit. Because the real one is stranger than kindness. It produced a star active enough to threaten, stable enough to sustain. It produced worlds that burned, worlds that thinned, worlds that hid, worlds that froze, worlds that tipped, worlds that leaked their oceans into space. It produced debris bright enough to look eternal and temporary enough to shame that impression. It produced an outer darkness populated not by one final symbol, but by remnants and survivors. And somewhere in the middle of that lawful severity, it produced one world that stayed open long enough for matter to wake up and notice the rest. That is not a comforting picture. It is a magnificent one. Because it means consciousness did not arise in a nursery. It arose in a system of thresholds, scars, and narrow survivals. We are not the children of a tame neighborhood. We are the brief awareness of a place that only looks peaceful after the worst of its formation has passed. And even then, only on certain worlds. Even then. Only for certain intervals. Even then. Only under balances so exact that nearby planets have spent billions of years showing us what would have happened if the terms had shifted. The oldest illusion was that the heavens were arranged for us. The harder truth is more beautiful. They were not arranged for us at all. They were arranged by gravity, heat, collision, chemistry, and time. And from that arrangement came a system full of failed versions, hidden versions, interrupted versions, and one version that remained permeable enough for life to become thought. The solar system did not owe us a habitable Earth. It produced one, briefly, lawfully, against a background of many other planetary answers that were harsher, narrower, or too unstable to carry the same burden. That is why the night sky changes once you really understand your own neighborhood. The lights do not become less beautiful, they become heavier. Venus is no longer just bright. Mars is no longer just red. Jupiter is no longer just large. Saturn is no longer just lovely. They become evidence. Evidence that worlds diverge. Evidence that atmospheres betray. That water hides. That gravity shapes possibility from far beyond the scale of ordinary intuition. Evidence that our own planet, which once felt like the unquestioned standard, is easier to misread than anything else because it is the one case we experienced before comparison taught us what it was. And so, the final realization is not that the solar system is full of secrets. It is that the deepest secret was always what Earth meant inside it. Not the center, not the norm, not the destination of the story. The narrow exception that held long enough to ask the question. And that is why, after everything, after the storms, the hidden oceans, the runaway heat, the stripped worlds, the stolen moons, the temporary rings, the unfinished edge, the most destabilizing thing the solar system reveals is not that other worlds are alien. It is that home was all along far stranger and far more fragile than it first appeared.